All right, good evening to all. Just let me screen this. Just 1 second. It is mirroring. iPad is mirroring. Yes. Right. Please confirm me, all of you. Audio, video, and other things are clear. All of you raise the hands. Right. So I think in the last class, I was discussing about the speed control techniques from stator side. And if I'm correct, we have finished two speed control techniques. One is the voltage control. The other one is the pole changing method. And in this, the voltage control can be used for both squirrel cage induction motors as well as slip ring induction motors. But whereas the pole changing method is applicable only to squirrel cage induction motor. Why? Because that rotor poles will automatically changes only in case of cage rotor, but not in slip ring. I hope this point is clear, right? Please confirm me all of you this. Right. Now let us see the other speed control techniques in case of stator side. What is it? Pure frequency control. Pure frequency control. Pure frequency control. So when I'm talking about pure frequency control, remember that we are keeping that voltage constant. So whenever I'm using the terminology pure frequency control, the voltage is kept constant here. So voltage is kept constant. Constant. Then if you see the equation for the rotor speed, Nr is equal to Ns into 1 minus S. So it is 120 into F by P into 1 minus S. So from this I can say the rotor speed is directly proportional to frequency, the supply frequency. So if you're trying to decrease the frequency, then the synchronous speed decreases, thereby the rotor speed decreases. And if you're trying to increase the supply frequency, the synchronous speed will increases, thereby the rotor speed will also increases. So what is the relation we are having between the rotor speed and the supply frequency is directly proportional. So this equation says that we can increase the speeds beyond its rated value. We can decrease the speeds below its rated value. Now let us see if I want to decrease the speed below its rated value, what I want to do for speeds below rated. For speeds below rated. For speeds below rated. Below rated. Then, so here when I'm talking for the below rated, so I'm decreasing the frequency so that the synchronous speed decreases, thereby the rotor speed also decreases. So here we are keeping this voltage constant. Why? Because I'm talking about pure frequency control. Then if you remember the equation for that phi r is directly proportional to V by F. I hope you remember this equation. As we are keeping this voltage constant, phi r is inversely proportional to frequency, right? Why? Because as of now we are not varying that voltage. So you can see, so when I'm decreasing the frequency so as to decrease the synchronous speed, thereby the rotor speed, immediately what happened to that air gap flux increases. So whenever we are trying to decrease the frequency to decrease the speed, the air gap flux increases. And you know that particularly in case of induction motor, we always try to maintain a smaller air gap. So it is something like in a small room which has a capacity to carry 10%. In that, if 1,000 persons have been like asked to adjust, so it is something like that room is crowded with the persons. So here in case of induction motor, we always try to maintain a smaller air gap. Now in the smaller air gap, as we are decreasing the frequency, so more amount of flux is going to be present. So because of this more amount of flux, obviously what happened to the cores now? Cores will get saturated. So both cores saturated. Both cores saturated. Both cores saturates. When I'm talking about both stator and the rotor cores saturate. So because of this saturation, core losses will increase. Core losses increases, right? So in order to supply more amount of flux, the magnetizing current will increase. When the magnetizing current is increased, so the machine will draw more reactive power from the source. When the machine is drawing more reactive power, the no load power factor will reduce, and at the same time, the operating power factor will reduce. So in order to supply more amount of magnetizing current, the no load current will increase. At the same time, the current drawn from the source will also increases. So when the current is increasing, what happened to that ohmic losses increases. Obviously, what happened to the efficiency of the machine decreases, right? So because of the increase in ohmic losses, what happened to the temperature increases. When the temperature increases, if the machine is operating with high temperatures for longer time, that insulation will start melting. When the insulation starts melting, then that a stage will come, complete insulation will melt, and life of the motor is going to be reduced. Life of the motor reduces. Life of the motor reduces. Then you can see here, so because of this pure frequency control, when you are reducing the frequency to reduce the speed, the machine performance is like damaging. So it is a purely unsatisfactory operation. It is a unsatisfactory operation. So it is true that we can reduce the speed, but with the sacrifice of the machine performance. It is purely a unsatisfied or unsatisfactory operation. So tomorrow, if anyone questions you, are the rotor speed and frequency holds the direct relationship. So by keeping the supply voltage constant, if you're decreasing the frequency, what happened to the synchronous speed decreases, thereby the rotor speed will also decreases. Absolutely, there is no issue in that. But whenever we are decreasing the frequency, then the air gap flux increases. As we are having a smaller air gap, more amount of flux will be accumulated, core losses will increase, saturation will take place. As a result, you can see the machine will draw high currents. Because of that, ohmic losses will increase, the temperature will increase, efficiency will decrease, and life of the motor will decrease. So it is a completely unsatisfactory operation. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So if anyone questions you, are a pure frequency control is a unsatisfactory operation or a satisfactory operation, then I can say it is a unsatisfactory operation for below rated. As of now, we have seen below rated. Now let us see for above rated. For above rated. For above rated. Above rated. So here I'm increasing the frequency so that the synchronous speed is increased. Thereby the rotor speed is also increased. As I'm talking about a pure frequency control, so voltage is kept constant here. Again, the same equation comes, phi r is inversely proportional to frequency. Whenever we are increasing the frequency, the amount of flux will decrease. Then T max, you know already, is inversely proportional to frequency square. Whenever the frequency is increased, T max is increased. T is inversely proportional to F cube. then starting torque will also decreases. Then you can see as phi r is decrease, E1 will decrease, then I1 is equal to V minus E1 by Z1. When E1 decreases, this difference increases, current on will increase again, ohmic losses will increase, again the temperature will increase, efficiency will decrease. So here you can see again the performance is a unsatisfactory performance. So can I say for above speeds or for below speeds, we are going to have a unsatisfactory performance. So even if you are varying the speed for below rated by decreasing the frequency, or you are increasing the speed by increasing the frequency, then you can see in both the cases we are having a unsatisfactory operation, right? So if anyone questions you, are a pure frequency control is a satisfactory control or unsatisfactory control, means by explaining all this, you can see it is a unsatisfactory control. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. So what happened to you? What about others? Right. Then if you ask how to rule out this problem of unsatisfactory control, so who is the main culprit for this, means I can say the air gap flux. This air gap flux. So this air gap flux. So if you want to have a satisfactory control, this air gap flux has to be kept constant. So if I want to keep this air gap flux constant, the ratio of V by F should be kept constant. So if I want to keep that ratio V by F constant, so whenever you are varying the frequency, proportionately you need to vary the voltage, so that V by F ratio is kept constant, and hence the air gap flux is kept constant, and hence the performance of the machine can be unchanged. So even if you are changing the speed, I hope this point is clear. Confirm me all of, confirm me all of. Right. So I say to rule out this problem, to rule out the disadvantages with pure frequency control, with pure frequency control, pure frequency control, V by F ratio should be kept constant, should be kept constant. For this, should be kept constant, so that air gap flux is maintained constant, maintained constant. For this, whenever frequency is varied to vary the speed proportionately, the voltage is varied to keep V by F ratio, and hence air gap flux constant, air gap flux constant. I think this point is clear for all of you. Confirm all. Raise the hands. Right. Now let us see how to keep this V by F ratio constant. Now I'll take this same example which I have taken in the last class. So I told you that in all speed control techniques, so take this problem. What is this problem? This problem. So what is the initial speed the motor is operating? 950 RPM. So what is the initial voltage you are applying? 400. And what is the initial frequency you are having? 50 hertz. Now let me continue. So here I want to decrease the frequency to 25 hertz. 25 hertz. So if you see here, what is that V by F ratio in this case? V by F ratio in this case is 400 by 50, that is equal to how much? 8, right? So here, in order to maintain that V2 by F2 again to 8, then what should be the value of V2? V2 is equal to F2 into 8. So that is 25 into 8, that should be how much? 200 volts. 200 volts. So I'm reducing the frequency from 50 to 25, and at the same time I'm decreasing the voltage from 400 to 200, so that the V by F ratio can be maintained constant, and hence the air gap flux can be maintained constant. Therefore, the machine should have a satisfactory operation. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. But in this case, if I want to calculate NR2, I cannot use this formula. I cannot use NR is directly proportional to F. Why? Because this is applicable only when frequency is varying. Applicable only frequency variations. But here we are changing both voltage and also the frequency. When applicable only for frequency variable. But here we are changing both voltage as well as frequency. In that case, right? In that case, see how frequency is changed. See, when I'm talking about frequency control, I don't understand why the people talk about voltage control. I never said that in case of voltage control, we are keeping V by F ratio constant. So when talking about frequency control, let me talk only frequency control. So I never use the terminology V by F should be constant in case of voltage control. And already I told you that is also an unsatisfactory operation, and we have seen the drawbacks with that voltage control. Please don't link both the things, right? And one more student told how frequencies change. See, you might be learning your so-called as power electronic devices. We are having cycloconverters, right? And using that cycloconverters, we can change the frequency. But as of now, I have not discussed how it is being varied. Just give me some time, you can understand, please. Right? So in this case, NR is directly proportional to F. We cannot use. Why? Because this is applicable only when you are changing frequency alone. But now you can see voltage as well as frequency both are changed. Then how to calculate the new speed, right? So here to calculate the new speed, I'll take this torque equation. Electromagnetic torque is equal to 180 by 2 pi ns S V square by R2. And already you know this equation. So it is 180 by 2 pi ns. In place of S, it is ns minus nr by ns into v square by r2. So in this you can see in ns there is one f. Ns is equal to 120 into f by p. Again in this there is one f. So if I just multiply f into f, so in the denominator you can see there are two frequency terms. So if I keep all other parameters constant, then you can see electromagnetic torque is equal to a new constant k dash into ns minus nr. In the numerator there is v square and in the denominator there is f square. Why? Because other parameters are numericals and the other parameters which are constant. So here electromagnetic torque is equal to some k dash into v by f whole square into ns minus nr, right? So here, what is the load the motor is driving? Means you can see the motor is driving a constant torque load, right? So here, the load torque is constant. The motor torque should remain constant. And at the same time, we are keeping that V by F ratio constant. So V by F ratio is also kept constant. Then if I keep all this, Ns minus Nr should remain constant. Should remain constant here. So from this, I can write ns1 minus nr1 is equal to ns2 minus nr2. So here, what is the value of ns2 means you can see ns2 is equal to 120 into f2 by p. So it is 120 into 25 by 6. It is how much? 500 rpm. Now I'll find out the value of nr2. So if I substitute ns1 is 1000 minus 950 is equal to 500 minus nr2. If I solve this, so nr2 will be 450 rpm. Like that, we can get the speed, right? So this question was asked in the previous computer examination and other computer examination for 2 marks, right? You can see that. Yes, I can see. Just 1 second. Now it is clear. Confirm me all of you. It is clear. My video not clear. Please raise the hands. Okay. Right. Now it is clear. Please confirm me. Raise the hands. Yeah. See, for 1 2 seconds happening, please try to adjust. Okay, anyhow. So this is the new speed. So this question was asked many times in the GATE examination, computer examination, and other exams also, right? So last before day, one of the student has shared this question, this type of question to me. So I told I'll give the answer in the coming days. Now you can see that person who has sent, you can just follow this procedure and you can calculate the answer for that. So how the question will be framed on this means, see, it is a three-phase 400 volts 50 hertz at a speed of 950 rpm driving a constant torque load. Full stop. The speed of the motor is controlled by V by F method. So whenever he is using the terminology V by F method, please remember that both voltage as well as frequency are varied. The speed of the motor is controlled with V by F method. What is the speed of the motor if the input frequency is reduced to 25 Hertz when the motor is driving a constant torque load? Then what is the answer for this? 450 RPM. I hope this point is clear. All of you confirm me. Confirm me, all of you. Confirm me, all of you. Right. So I told you that for every numerical, for every speed control technique, we have two models. One is, if you look into that voltage control, initial voltage is 400. When you are reducing the voltage to 300, the speed you have calculated. The other type of numerical is the speed is 950 and I want to reduce the speed to 10%. What is the voltage required, right? These are the two possible questions. If you refer any computer examination, either this side or that side, the question will be given. So here we have reduced the frequency to 25, then we have calculated what is the speed, right? Now other type of question is, I want to reduce the speed by 10%. In that case, what is the frequency required? And for satisfactory operation, what is that voltage also required, right? Please find out. Write down. For the above problem, for the above problem, for the above problem, calculate the frequency required to reduce the speed by 10%. 10%. For satisfactory operation, what is the value of voltage? Voltage required. Please do it. I'll give 2 minutes time. Do it. It's a condition. When the motor is driving, driving a constant torque load, right? Do it. Please, I'll give 2 minutes time. Do it, all of you. Do it. I'll give 2 minutes time. .25 surgencing and 362 volts, right? Very excellent. So let me do it. So all of you, please. So what is the speed? NR2 is equal to 950 minus 95, 10%. Means it should be 855 RPM. Then as the motor is driving a constant torque load, NS1 minus NR1 is equal to NS2 minus NR2. So it is 1000 minus 950 is equal to what should be the value of NS2, so that the speed is 855 RPM. So 50 is equal to NS2 minus 855. From this, NS2 is equal to 905 RPM. And you know that NS2 is equal to 120 into F2 by P. So from that, F2 is equal to 905 into how many poles? 6 by 120. So what is the answer? So it is 45.25 according to you hertz. Then for satisfactory operation, V2 by F2 should be equal to how much? 8. So from that, what should be the value of V2? 8 into 45.25. So what is the value for this? It is 362 if I am correct. Please check. 362 volts. So this is something about your answer. Is it clear? Please confirm me. All of you raise the hands. Please confirm me. All of you raise the hands. Right. The next one is for above rated frequencies. For above, right. One more thing. You can see as V by F ratio is kept constant. So I can call this method as V by F control. Or it is also called as constant flux control. This is also called as variable voltage, variable frequency control. And I can call it as V into 1 by F, that is volt second control. This I can call it as volt second control. So tomorrow in your examination, if any one of these four terminology is used, then you have to understand that V by F ratio is kept constant. He will not say frequency is varied, proportionately voltage is also varied. He will not use that terminology. He will say that whenever the frequency V by F ratio is kept constant, means with the frequency, voltage is also varied. I think this point is clear. Confirm me all of you. Right. Done. Next one is for above rated speeds. Rated speeds. So we'll be discussing more on this in your power electronics, right? Speed control techniques. So here we are giving only the background, right? For above rated speed. So here, for example, say I'm increasing the frequency to 75 hertz. I want to increase the frequency to 75 hertz. Then for that, what should be the value of V2 by F? It should be 8. Then V2 should be equal to 8 into 75. It has to be how much? 600 volts. So if I want to have a satisfactory operation, so with the frequency, I have to increase the voltage to 600 volts. But you know that the rated value of this motor is 400 volts. We are not supposed to apply voltage beyond 400 volts. If you are applying more than 400, what happened to that insulation will get damaged. So in this case, we are not able to increase the voltage proportionately. So here we are fixing this voltage to only 400 volts. So please remember that in case of above rated speeds, as we need to increase the voltage beyond its rated value, so it is not possible to increase the voltage beyond its rated value. Why? Because that insulation is going to damage. Then what is the safest voltage we can apply? Means it is only the 400 volts. Beyond that 400 volts we cannot apply. So here V2 by F2 cannot be 8. So here we are varying only frequency, but which parameter is kept constant? Here voltage is kept constant, and here flux will not remain constant. So for above rated, we are going only for frequency control, but not for V by F control. So in this case, what is the relation that will hold good? Means it is NR is directly proportional to F. But here we have a satisfactory control or unsatisfactory control. Means we have only a unsatisfactory control. We cannot have a satisfactory control, right? Please remember that satisfactory control is possible only when area flux is kept constant. For that V by F ratio has to be kept constant, but here we are changing only frequency, keeping that voltage constant, and hence it is not possible for a satisfactory operation in this case. I think this point is clear. Confirm me. Right, fine. So here the speed will be increased, but it will be an unsatisfactory operation. So one question, sir, ns minus nr is kept constant when torque is proportional to slip. I never said torque is proportional to slip. I told you that when the motor is driving a constant torque load, then ns minus nr should remain constant, right? See, please try to go through the basics, okay? Don't think whatever you think. See, I never said ns minus nr is kept constant when torque is proportional to slip. See, whenever we are talking about speed control techniques, please remember the value of slip is always low. So when the motor is operating, when the motor is running, it should be always closer to ns. Please remember that the slip value will be always less, right? So here, this method we can call it as a pure frequency control. Pure frequency control, or here phi r is inversely proportional to f. As you are increasing frequency, then what happened to flux decreases. So this we call it as a flux weakening method, flux weakening control. Just like in case of your DC motor, by varying the field current, by reducing the flux, the speed of the motor can be increased. In the similar way, we can increase the speed here, right? So this is something about the speed control by varying the frequency. Let me again proceed with. So we have seen that NR is directly proportional to F. So by varying the frequency, we can vary the motor speed. So if I am reducing the frequency to reduce the speed by keeping that voltage constant, we have seen that we have a unsatisfactory operation. Even we are increasing the frequency to increase the speed, we had a unsatisfactory operation. So who is the main culprit for this unsatisfactory operation? Means the air gap flux. So if you want to have a satisfactory operation while you are controlling the speed by this frequency control, so V by F ratio and air gap flux has to be kept constant. For this, whenever you are varying the frequency, in addition to that you have to vary the voltage also, but that is possible only when you are varying the speeds below rated. Why? Because you are reducing the frequency, we can reduce the voltage, but for above rated it is not possible. So whenever I am using the terminology V by F control, means please remember that it is only for the speeds below rated but not for the speeds above rated. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right, done. Now the question comes how to get a variable frequency, that we'll see, right? So drawbacks. First note is This method is applicable to both squirrel cage induction motors and slip ring induction motors. We can use for both the cases. Drawbacks. What are the drawbacks we have means? Let me explain the drawbacks. So if I'm taking a three-phase induction motor, so it is generally fed with a constant voltage and constant frequency generally. But as I need to vary the speed by varying the voltage and by varying the frequency, then the input to that motor should be a variable voltage and variable frequency. For that, what I will do means I'll convert that fixed AC at fixed frequency to a DC with the help of a converter. Again, the DC is converted back to AC, right? And with a variable voltage and variable frequency, and that is fed to this induction motor. So this is a converter and this is the inverter. Like that, we can convert fixed voltage and fixed frequency AC to a DC, and from the DC we can use an inverter, and from that inverter we can vary the magnitude of the voltage and also the frequency, and that variable voltage and variable frequency can be fed to that induction motor for controlling the speed. So as we need these converters and inverters on the stator side, the cost will be increased. So due to this converters and inverter, the overall cost of the machine will increase. I think this point is clear. Please tell me. Right. So Vishnu Ajit told, sir, for V by F method, he is not applicable for more high speeds. No, I am not talking about high speeds. I'm talking for the speeds more than rated. So when you are increasing the voltage more than rated voltage, it is not possible. Why? Because the insulation will get damaged. Vishnu, is it clear? Vishnu Ajit, raise the hands. Vishnu Ajit. Okay, right. Done. So this is something about your stator side control. So let me once again revise and repeat. So we have seen the three speed control technique from your stator side. One is the voltage control, the other one is the pole changing method, the last one is the frequency control. So in that pure frequency control, we have some drawbacks, some disadvantage. So that is the reason we need to go for V by F control. Among these three methods, I can say as of now, the only satisfactory method is nothing but your V by F method, and that too only for the speeds below rated but not for the speeds above rated. So as of now, if anyone questions you, you have discussed voltage control, pole changing method and frequency control. Among these methods, which one is a satisfactory control means I can say V by F control, and that too it is only for the speeds below rated but not for the speeds above rated. Why? Because if I want to increase the speeds above rated, proportionately I have to increase the voltage, which is not possible. So for that we go only for below rated speeds. I think this point is clear. Confirm me all of you. Right, done. The next one is rotor side control. Right, see for below rated, see please Imtiaz Pasha, when you are keeping that V by F ratio constant, please remember, right, whenever we are keeping that V by F ratio constant, T max will be constant. Pasha, you please try to remember that. Fine. So anonymous attendee has thrown one interesting this one. Sir, I'm very sorry to say that I'm getting sleep whenever I listen to the online classes. How can I overcome this, sir? Please help me. See, the only thing is a physical way of learning and online way of learning is 100% different. So if you are having a zeal to learn, then you should overcome this. Please remember that, right? Please. Oh, one more student has given the answer for that. Sir, tell him to eat chili, sir. Okay. So I think this is good. Good. So eat chili. So you'll not get sleep. Excellent answer by another anonymous attendee. Right. Fine. Done. So we'll proceed. So this is something about right, Baba. See, one thing, I strongly believe that, I strongly believe that. So everything is in our own hands. I strongly believe that. If you want to be good in job, if you want to be top in position, if you want to ruin your life, if you want to spoil your life, if you want to degrade your life, it is here only. If you say because of somebody X, I was being spoiled, in it is a meaningless argument. It is a meaningless decision, right? So everything lies in our own hands. Please remember that. So I have seen many of the students in my past 15 years teaching experience, those who has scored top BTech, students are also university topper. They could not qualify even GATE exam also, right? It is true. The main reason for that is, the main reason for that is they have the overconfidence. So please overcome that, please. Right. So one more, how do they even get sleep in the interesting sessions? So it is up to him, Baba. I cannot answer to that person, right? It is a meaningless comment, meaningless things. Anyhow, fine. Anyhow, we'll come back. So one or two will be there. So we'll be like spoiling the mood of a teacher and also the class. I'm not bothered about that, right? Listen. So I hope you have completed the status set. Is it clear? Confirm me all of you. Confirm me all of you. Right. Done. The next one is the rotor side control techniques. Rotor side control techniques. Rotor side control techniques. Rotor side control techniques. Control techniques. Rotor side control techniques. Please remember that these rotor side control techniques are applicable only to slip ring induction motors. Only to slip ring induction motors. Only to slip ring induction motors. Why only to slip ring induction motors means only in case of slip ring induction motor. So we have the provision to vary, to alter the rotor circuit parameters. Whereas in case of squirrel cage induction motor, we don't have the provision of altering or disturbing the rotor circuit parameters. Why? Because the rotor bars are permanently shorted or the rotor bars are permanently short circuited. So these are applicable only to slip ring induction motor. See, please confirm me, one or two are raising the hands again. So is my voice, audio and everything are clear? Confirm me once. Right. So some say clear. Once again, let me just switch off the video and I'll come back. Now clear? Confirm me. Now clear? So this video will be taking more data. That is anyhow. So rotor side control technique, these are applicable only for the so-called as slip ring induction motor or slip ring rotor. Now in that, the first one is the rotor resistance control. So this is an important thing, rotor resistance control. Rotor resistance control. Right. So in case of rotor resistance control, please remember the main point is we are not changing the original resistance R2. The R2 is kept constant. But by adding some additional resistance R external, the total resistance of the motor winding is changed. Please remember, in case of rotor resistance control, we are not changing the original rotor winding resistance R2 by varying the additional resistance which we are adding in the rotor circuit, we are varying the speed, right? Please remember that. Is this point clear? Confirm me all of you. Right. So in this, voltage is kept constant, frequency is kept constant, number of poles are kept constant, the leakage reactance is also kept constant. Like that, everything are kept constant. Only the resistance is varied. Then if you take this torque equation, electromagnetic torque is equal to 180 by 2 pi ns s v square by r2. So here you can see the frequency and poles are constant, ns is constant, and this is also constant. You can see we are not changing the voltage. Voltage is also kept constant. So from this I can see the electromagnetic torque is directly proportional to S by R2. S by R2. Then here, what is the load the motor is driving? The motor is driving a constant torque load. Then in that case, S by R2 should remain constant. Should remain constant. So from this, can I say S is directly proportional to R2, and you know NR is inversely proportional to S. Then can I say by adding some additional resistance in the rotor circuit, I can increase the slip. So when I can increase the slip, then the speed of the motor can be reduced, right? I think this is a relation what we had between the rotor resistance and the slip and the speed. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. Done. Now let us take a numerical. So what is the value of R21? The previous class, yesterday's class, if you recall. So here you can see R21 is equal to 0.1. So R21 is equal to 0.1 ohms. How many pole machine? 6 pole. Then what is the synchronous speed in this? 1000 RPM. Then what is the rotor speed in that case? NR1 is equal to 950 RPM. Then what is the slip? S1 is equal to 0.05. Right? Now what I'm trying to do means I'm trying to add an additional resistance of one more 0.1 ohm. Then what will be the value of R22? R22 is equal to R21 plus R external. So that is zero point 0.1 plus zero point 0.1. This is equal to 0.2 ohms. Then which ratio has to be kept constant? S by R2 should be kept constant. Why? Because the load is constant here. So from this, S1 by R21 is equal to S2 by R22. So from this, what is the value of S1? 0.05 by zero point 0.1 is equal to what is the value of S2 by 0.2. So from this, S2 is equal to how much? 0.1. Then what is the value of NR2? NR2 is equal to NS2 into 1 minus S2. As you can see, we are not changing frequency and poles. Then here NS2 will remain same. Why? Because frequency and poles are same in this case. Then that is equal to 1000 into 1 minus zero point 0.1. So it is how much? 900 RPM. 900 RPM. I think this point is clear. Confirm me all of you. Confirm me all of you. So can I say by adding a resistance of 0.1 ohm additional in the rotor circuit, the speed of the motor is reduced to from 950 RPM to 900 RPM. Like that we can reduce the speed. I hope this point is clear. Confirm me all of you. Confirm me once. Right. I told you that for every numerical there are the other side also. What is that? So here the initial resistance is 0.1. I'm adding an external resistance of 0.1, then what is the speed? The other question is the initial speed is 950 RPM and I want to reduce the speed by 10%. In this case, what is the resistance to be added, right? Why late? You do it for the above problem. For the above problem. For the above problem. Calculate the additional resistance required in the rotor circuit to reduce the speed by 10%. Do it. I'll be waiting. Just I'll give. When the motor is driving a constant torque load. When the motor is driving a constant torque load, please. A constant torque load. Right? Do it. 0.19, Abhijit. 2.9. See, 0.19 is correct. Right, Abhijit. Ramakrishna, please subtract 0.1. It is not 2.9. So here, what is the value of NR2? Just I'm writing directly 855. Then what is the value of slip? It is 0.145. Then R21 by, sorry, S1 by R21 is equal to S2 by R22. R21 is how much? 0.05. Sorry, S1 is 0.05. R21 is 0.1. S2 is 0.145 by I need to calculate R22. Then what is the value of R22, which is R2 plus R external, that is 0.29. So from that, R external is equal to 0.29 minus 0.1. So it is 0.19 ohm. 19 ohm. I hope it is clear. Confirm me all of you. Confirm me all of you. Right. See, one question was asked by one of the student, Vishnu Ajit. Sir, when slip is varied, relative speed varies, right? Then I2 also varies. So in this case, obviously, whenever the slip is varied, the relative speed varies, current varies, ohmic loss varies, then again, this is applicable only for short time. I'll tell that in the drawbacks. Don't worry. Fine. So this is something about your, which one? The rotor resistance control. So how can I say, see, if I take this electromagnetic torque, it is 180 by 2 pi ns S V square by R2. So here what is that we are trying to do? We are trying to increase the resistance. Whenever we are trying to increase the resistance, what happened to the motor torque? The motor torque will decrease. So whenever the motor torque decreases, what happened to the speed? Decreases. When the speed decreases, again what happened to the slip? Increases. So due to the increase in slip, what happened to the motor torque? Increases. So up to level the slip will increase means when both parts are cancelling, or whatever reduction we have in the torque, it is compensated by that increase, so that this will remain constant, right? So because of the increase in slip, what happened to the speed? It is decreasing. So if anyone questions you, in case of resistance control, what is that you are doing is, by adding some resistance in the rotor circuit, we are making the electromagnetic torque to decrease. When the electromagnetic torque is decreased, the speed will decrease. When the speed decreases, obviously what happened to the slip increases. Again, with the increase in slip, the electromagnetic torque will increase. So a situation will come that both the torques will begin same at a new speed, right? I'll explain this with the help of a torque slip characteristics. I hope this is clear. Confirm me all of you. Right, I'll explain this with the help of a torque slip characteristics. Give me 1 minute time. So I think we have seen the family of torque slip characteristics with the different resistances. Different resistances. Already we have seen that. So let me draw for one resistance here. This is for one resistance R21. Now let me draw for the other resistance R22, which already you know how to draw. This is R22. Then I'll take one more resistance R23. So don't ask her how to draw this. Already we have drawn this in the previous classes. R23. So these are the family of torque slip characteristics with the different resistances. This was already drawn in the last class. So assume that the motor is driving a constant torque load. Which load the motor is driving? A constant torque load. Right, done. C. When the resistance is R21, you can see when the resistance is R21, then you can see this is the point of intersection, that is the speed NR1, which is a stable speed. It is 950 RPM. This is what we have seen. Up to here, clear? Please confirm me. Confirm me. Right. So what is that I'm trying to do now means I'm trying to increase the resistance. If you take electromagnetic torque, it is K into S into V square by R2. So whenever I'm increasing the resistance by adding some additional resistance, immediately what happened to the electromagnetic torque decreases. So this electromagnetic torque will fall from here to here, will fall from here to here. So when the resistance is R2, then NR1, which is 950 RPM, is not the stable speed. Why? Because here the motor torque and the load torque both are not same. So which torque is less here? The motor torque is less than the load torque. When the motor torque is less than the load torque, then the motor will decelerate. At a new speed of NR2, when both the torques are constant, then the motor will run with that speed of NR2. I think this point is clear. Confirm me. This was already explained in voltage control. Confirm me, all of you. Still, if you are adding the resistance, what happened? These characteristics will fall and the point will be somewhere here. It will be like this. So can I say whatever the reduction we have in the motor torque because of adding of resistance, that is been compensated by the increase in torque due to the increase in slip. So when these two torques are same, then with a new slip, with a new speed, the motor will rotate. So can I say like this? By keeping the supply voltage and frequency constant, if the resistance is added in the rotor circuit, the slip increases to maintain the constant torque. Why? Because why the slip has to increase means the load on the motor is constant, the motor torque should remain constant. So in order to maintain that motor torque constant, whenever the resistance is increased, the slip has to increase. How the slip will increase means when you are adding a resistance, the electromagnetic torque is decreasing compared to the load torque, then the motor will decelerate. Then with the deceleration, the slip is increasing. So this increase in slip will continue till both the torques are becoming same. When both the torques are becoming same, then the motor will continue to rotate with that particular slip with that particular speed. I hope this point is clear. Confirm me. Right. So can I write a note here? Can I write a note here? Right. Can I write a note here? What is that? By keeping supply voltage and frequency constant, if the rotor resistance is increase, the slip increases, to keep torque constant. As slip increases, the speed of the motor decreases. I think this is clear. Confirm me, all of you. Confirm me, all of you. Raise hands. Right. Then drawbacks. Drawbacks. So here we have the provision of only adding resistance. We cannot reduce that resistance. So when we can add the resistance, only the slip can be increased. When the slip is increased, the speed of the motor can be decreased. So here, below rated speeds are possible. Below rated speeds are possible. Speeds are possible. Possible. So whenever we are adding resistance, the speed is decreasing. When the speed is decreasing, the relative speed between the field and the rotor conductors is increasing. Then flux cuttings will increase, EMFs in the rotor conductors will increase, currents will increase, ohmic losses will increase, temperatures will be very high. For that, it is not applicable for long time, it is only for short time. Why? Because adding resistance will increase the ohmic loss, temperature will rise, and if it is there for long time, the windings will get damaged. So it is applicable only for short time applications. Short time applications. Here, please remember, whenever we are talking about slip control, the synchronous speed is constant. Keeping that synchronous speed constant, if you are trying to take the rotor speed away from that, then even a small change in the flux cuttings will induces more EMF in the rotor circuit. More currents will flow. So if you remember the torque slip characteristics, when the speeds are very closer to that, then the flux cuttings will be less, the EMFs will be less. But if you're trying to take little bit away, flux cuttings will increase, currents will increase to enormous value. So for that, this method is not applicable for wide range, it is only for narrow range. Please remember, whenever we are talking about slip control, we are not supposed to take the rotor speed away from the synchronous speed. If you're trying to take the rotor speed away from synchronous speed, then that losses will be high, the windings will be damaged in very short time. So for that, it is not applicable for wide range, it is only for narrow range. It is for narrow range of speed control. Narrow range of speed control. So this is something about your resistance control. Let me once again repeat. Whenever I'm talking about resistance control, please remember, we are not changing the original rotor winding resistance R2. That original rotor winding resistance is kept constant. We are not varying that. But what is that we are varying means, we are varying the total resistance of the rotor winding. That is, by adding some external resistance, we are varying the total resistance, right? Is this point clear? Confirm me. Confirm me. So here we are not changing voltage and frequency. Voltage and frequency are kept constant. We are not varying that voltage and frequency. Voltage and frequency are kept constant. So here, whenever we are adding the resistance, then obviously what happened to the motor torque decreases. So from stable operating point, when this load torque and the motor torque are same, then the motor will be running stably. But whenever you are adding resistance, what happened to this motor torque decreases. When the motor torque decreases, obviously what happened to that point becomes unstable. Why? Because the load torques and the motor torques are not same. As the motor torque is decreasing, as the load is dominating, then the motor will decelerate. The speed will decrease. When the speed is decreasing, what happened to that slip increases. With the increase in speed, again what happened to the motor torque increases. So the increase in slip will continue till again TEM and TL should become same. Again TEM, TL become same, then the motor will continue to rotate with that new speed where both TEM, TL are same. Right? Like this, the resistance is going to vary the speed. I hope this point is clear. Confirm me, all of you. Right. So this is something about your resistance control. The next one is by injecting EMF. So before we proceed to the other topic, let me tell few things. If anyone questions you, do you know the basic constructional details of a induction machine? Yes. What are those? It consists of a frame. It consists of two codes. It consists of slots. It consists of windings. We have learned the different types of slots and other things. We have learned the basic construction details of induction machine. Is this point clear? Confirm me. Right. If anyone questions you, Are Baba, you know about the working principle of an induction motor? Yes. Do you know the concept of the relative speed between the fields and the conductors? Yes. Do you know the concept of the load angle? Yes. Please confirm me this, all of you.
Right. Next one is, without a physical motor, is it possible to find out? Is it possible to find out the performance of an induction motor? Yes. How? Means, if you know the rotor circuit parameters, I'll give the approximate values. If you give both stator circuit as well as the rotor circuit, I'll give the exact values, right? So using that rotor equivalent circuit or using that complete induction motor equivalent circuit, I can find out the complete analysis. Can you find out? Yes. Please confirm me. Is it clear? Right. And the other in is, you know the torque slip characteristics of an induction motor. Yes, the starting torque will be less, but with the increase in speed the torque will increase. After reaching the maximum value the torque will decrease. So I know the torque slip characteristics, as the induction motor characteristics are also raising torque characteristic. In most of the applications we use these induction motors for raising loads, right? Fan loads, mixer loads, constant torque load we use in that particular case. Is this point clear? Confirm me. Raise hands. Right. The induction motor which you have designed, which you are discussing, will be drawing very high currents at starting. You know the reason for that? Yes. Can you please tell me how to control such high starting currents? Yes. We have learned about the starting methods. Please confirm me. Confirm me. Right. I want to use the induction motor for variable speeds. Can you please tell me the speed control technique? Yes. Now we are discussing. Then I answered to that person. See, the speed control of a three-phase induction motor is generally very difficult, but with the invention of this power electronic converters or power electronic switches, the speed control becomes little bit easier. It is little bit easier. Now we have seen the speed control techniques from stator side. Right. I'll list out some drawbacks of a induction motor. What are the drawbacks of an induction motor is, the first drawback is the stupid induction motor always draws the lagging current. It always operates with lagging power factor. Can anyone tell? Yes. Why? Because this three-phase induction motor is a single excited motor. As it is a single excited motor, to produce the rotating magnetic field, it needs a reactive power, and that reactive power is drawn from the same source from which it is drawing the active power. As the same source is supplying both active as well as the reactive power, the operating power factor of an induction motor will be always lagging. There is no chance that it can be leading. I think this point is clear. Confirm me. But whereas the power factor of a synchronous motor can be varied. Why? It is a double excited motor. So the stator is connected to a three-phase source, whereas the rotor is connected to a DC source. That means that that synchronous machine can get the reactive power either from the rotor side or from the stator side. If the rotor is not able to supply the required reactive power to produce the field, it draws it from the source, operates at the lagging power factor. If the rotor is able to supply the required reactive power to produce the field, it will not draw any reactive power, it will operate with unity power factor. If the rotor is able to produce more reactive power, then it will supply a part of the reactive power into the source and it will operate at leading power factor. That means a synchronous motor can be operated in leading, lagging as well as in unity power factor. Is it clear? Raise the hands. But induction motor will always operates with lagging power factor. Why? Because it is a single excited machine. It will draw the reactive power from only one source from which it is drawing the active power, and hence it will always operates with a lagging power factor. This is the main problem we are having with induction motor. The second problem is this induction motor cannot be operated with the speeds away from synchronous speed. For that reason, it is designed for a constant speed operation. We cannot use for this for a variable speeds. Why? Because keeping that ns constant, if I'm trying to take the rotor speed away from ns, then the slip will increase, the currents will increase, ohmic losses will increase, windings will get damaged. For that, we cannot use the induction motor for a variable speeds. Then for that, I'll you answer no, 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 no. With the invention of these power electronic converters, I can give a satisfactory operation with induction motor. Even I can vary the speeds. If I'm having a variable voltage and variable frequency operation, I can have a satisfactory operation in that case. Of course, the remaining may not give a satisfactory operation, but with variable voltage and variable frequency, as ns minus nr is kept constant, current will be constant and the performance will be constant. So there is no much issue. Even I can say this induction motor can be used for a variable speeds, right? variable speeds if you are having a V by F control. But some say it is applicable only for below rated, it is not for above rated. Is this point clear? Is this point clear? Confirm me all of you. Right. Done. Now, whatever the method I am trying to discuss now, by injecting an EMF in the rotor circuit. 1 second. Right. I'm back. Right. So if anyone questions you, Arey, how to control, if anyone say, Arey, a three-phase induction motor cannot be used for variable speed operation. Arey, you stupid fellow. I know how to operate a three-phase induction motor with variable speed operation. If you are having this converters and inverters, I can use that converters and inverter to control the speed. So I can have a satisfactory operation with that induction motor, right? Can you please confirm with me? Raise the hands. But, 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 what is the other one is, whatever that V by F method we have discussed, it is not applicable for above rated, it is applicable only for below rated. And one more thing is, your induction motor always operates with lagging power factor. So using that V by F method, we cannot operate the motor unity, or we cannot operate the motor even for leading cases. Now, whatever the method we are trying to discuss now, this EMF injection method. So using this EMF injection method, we can vary the speed of an induction motor in very wide range, right? Below synchronous, away from synchronous, or above synchronous, right? More than synchronous, we can operate. At the same time, we can improve the power factor of the motor also. That means just like in case of your synchronous motor, we can make that induction motor to operate in leading power factors. Even we can operate induction motors at lagging power factors or unity power factors. Just like your synchronous motor, your induction motor can be made to operate with leading, unity, and also lagging power factors. And we can vary the speeds below rated, away from synchronous speed, above rated, like this side, positive side, negative side, we can operate in sub-synchronous or synchronous speed also. So tomorrow, if anyone questions you, are the three-phase induction motor which you have discussed always draws a lagging power factor and it cannot be used for a variable speed operation, then I can say no, 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 no. I have one speed control technique. Using that speed control technique, I can use this induction motor for variable speeds without sacrificing the performance of the motor, and even I can improve the power factor of an induction motor, like lagging to unity, unity to leading. I can improve just like a synchronous motor, right? This is what we are trying to see in EMF injection method. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. So the next concept is EMF injection method. So EMF injection method. EMF injection method. See, one student, Shiva Gopi Raju, it is possible to deliver the reactive power by capacitor banks. Yes. But see, what is the main problem we are having with a capacitor bank means the values of capacitance are fixed. So they can supply a fixed reactive power, but the load on the motor is varying, and basing on that, the reactive power demand on the motor will be varying. So for that, we cannot do that. Sir, can we control the speed above synchronous speed in AC Yes, sir, that's what I'm trying to tell, right? Please, I'm trying to tell it can be used for above also. Please remember that. Right, done. I'll explain this, please. Right, please. So EMF injection method. EMF injection method. Second one is by injecting. This is a very, very important thing. See, one of the student type, so tomorrow will the last class for induction motor. Please don't be that much hurry. I'm not complete your syllabus. I'm here to complete your subject. If it is required, I may take one more day or one more session. But please remember that. Don't worry about your number of days. So that will be done. That will be taken care of me and my manager. Don't worry. By injecting EMF in the rotor circuit. In the rotor circuit. Rotor circuit. See, in Vijayawada, since yesterday, there was a huge rain, right? So there was a huge power issues here. But in order to not to waste a single day of your class, I have arranged many things. Why? Because I know the value of single minute, right? Even if there is no power, if I'm not using this UPS, that is inverter, then I may miss one day. So one day matters more for me. So my intention is my students should not miss a single day because of the power issues. So for that, I'll have a backup every time. Please remember that. Fine. So what is that EMF injection method, right? EMF injection method means, right? EMF injection method means it is not like I'm taking a syringe and I'm using that syringe to take some voltage, I'm injecting in the rotor circuit. No, no, no. EMF injection method means, so we are giving one more three-phase supply to the rotor circuit. One more three-phase supply to the rotor circuit we are trying to give, right? Please. So what is that EMF injection method means? Giving one more excitation to the rotor circuit at slip frequencies, at slip frequencies, at slip frequencies, right? See, one small request. Some are again raise the hands. Is my audio, video, everything are clear? Please type. Voice is breaking. See, Baba, give 2 minutes time. Again, I'll switch on, switch off, and switch on. So I'll take 2-3 minutes. Just be aware. Why? Because same had just 2 minutes you give. Now confirm me, all of you, it is clear. Right, done. So what is that injecting an EMF in the rotor circuit means? We are giving one more excitation to the rotor circuit. But remember that what is the frequency at which we need to give the excitation to the rotor circuit means it should be always at a frequency of SF, right? Now let us draw before injecting an EMF. Please see. Before injecting an EMF, please. So I'll draw the schematic or a block diagram. So I'm having a three-phase supply. Right? This is a three-phase supply. What are the parameters? 400 volts, 50 hertz. Then I'll be taking a three-phase induction motor. What are the values? R2 is equal to 0.1, X2 naught is equal to 0.85 ohms. This motor, as it is a slip ring, assuming that, why? Because we are talking about the resistance control. These are the three slip rings, and here we are not using any external resistance here. These external resistance are not there. So whenever I'm giving a three-phase supply to this motor, as it is a 6-pole motor, what is the synchronous speed? 1000 RPM. What is the rotor speed? 950 RPM. What is the slip at which it is operating? 0.05. What is the load it is driving? A constant torque load. Right? Is this point clear? Confirm, all of you. Right. Now, what is a rotor equivalent circuit? A rotor equivalent circuit. So, if you remember the rotor equivalent circuit, what is the voltage here in the rotor? E2. What is the impedance? Z2. And the rotor circuit is closed here. Why? Because we are not adding any external resistance or anything. The rotor circuit is closed. Let us consider this E2 value is equal to something like 10 volts. This resistance is something like 2 ohms. What is the current that is flowing? It is 10 by 2. It is 5 amperes. Current is flowing in the circuit. Now let me draw the phasor diagram. So what is that phasor diagram? If this is V1, this is I naught, this is I mu, because of this there is one flux, and this is E2, because of that there is I2, because of I2 there is one flux, phi 2, to compensate that the machine will draw I2 dash, this is I1, and the angle between this V1 and I1 is theta 1. So these are the operating condition. So whatever the motor we have considered now, this is the motor. What is the excitation we are giving to that motor? 400 volts at 50 hertz. What is the speed at which the motor is operating? 950 RPM. What is the slip at which it is operating? 0.05. Then the motor is driving a constant torque load, right? Now let me assume that this angle is something like 30 degrees, something like 30 degrees. Then cos of 30, that is 0.866 something. The power factor is this much. So this is the operating power factor of that motor. Up to here, clear? Clear? Right. So who is driving the current in the rotor circuit? Who is driving the current in the rotor circuit? E2. So I2 is equal to E2 by Z2. right? So where E2 is the EMF induced in the rotor winding, in the rotor winding due to flux cutting, due to flux cuttings. So from this, E2 is equal to I2 into Z2, and you know E2 is equal to S E2 naught is equal to I2 into Z2. From this, S volt is equal to I2 into Z2 by E2 naught. Let me take this value to be 0.05, right? Why? Because what is the literal value of slip here? 0.05, and I'm taking that to I2 into Z2 by E2 naught. So this is something about the so-called as the operating parameters, operating conditions. Now we have not discussed any speed control technique by injecting an EMF. This is a situation when we are giving a voltage at 400 volts, 50 hertz supply. Is this point clear? Confirm me, all of you. Confirm me. Right. Still, all. Now let me take some numerical values also. What is that? This is drawing a active power of 10 kilowatts and reactive power of some 2 kVAr. So why this active power is required means to turn the rotor, Why this reactive power is required means to produce a rotating magnetic field. So these are the values. Let me assume that, right? Done. So now what I am trying to do means I am trying to inject a voltage. What is the meaning of injecting a voltage means giving one more excitation to the rotor circuit. But what is the frequency at which I need to give the excitation? Means it is at a frequency of SF. So here, so for SF, what I'll try to do means I'll try to take a converter here. Why I need a converter means to convert that AC to DC. Then I need an inverter here. Why I need that inverter means to convert the DC back to AC at a frequency of SF. Let me say the injected voltage is EJ. So what is the voltage you are giving to the rotor circuit per phase? EJ at a frequency of SF, right? Now I'll draw the equivalent circuit after injecting an EMF. Rotor equivalent circuit after injecting EMF. Injecting EMF. So one side, the rotor conductors are getting the voltage due to flux cutting. On the other side, those rotor conductors are given with some voltage, EJ, EJ, right? So this is the injected voltage. This is Z2. Then who decides this current I2 means it is not the EMF due to flux cutting. It is due to the algebraic sum of the EMF due to the flux cutting and also due to that excitation or one more excitation that is given to the rotor voltage or rotor circuit. So here I2 is equal to E2. See, Baba, please be patient. So 1 or 2 who is getting that sleep, please try to wake up, have one chilly and try to be alert here, please. Why? Because if you refer in textbooks, in no textbook, this concept will be clear. Please try to sit more patiently, right? E2 plus or minus EJ by Z2. So if anyone questions you, who is circulating the currents in the rotor circuit after injecting the voltage means I cannot say it is the injected it is not because of only the EMF due to flux cutting. It is due to the sum of the EMF due to flux cutting and also that injected voltage. So the resultant of these two voltages are circulating the current in the rotor circuit. Is this point clear? Confirm me. Confirm me. Right. So what is that plus minus? I'll explain, don't worry. So here E2 plus or minus EJ, that is equal to I2 into Z2. So here this E2 is EMF due to flux cutting, and this is
the injected voltage, injected voltage, injected voltage, right? This is something about your after giving that excitation to the rotor circuit, right? Done. Now I'll be discussing 4 cases in this. Please be alert. 4 cases. Case 1, if an EMF at slip frequency is injected in phase with the existing rotor EMF, existing rotor EMF. What is the meaning of in phase? See, if this is the rotor voltage E2 at a frequency of SF, so whatever the voltage I'm trying to give should have the same phase. This is EJ. Then the resultant will be E2 plus EJ. So this is the resultant voltage. This is the resultant voltage. I hope you understood what is the meaning of same phase. Is this point clear? Confirm me. Is this point clear? Confirm me. All. Only few. Right. Done. Then what happened? I'll take this equation. I'll take plus. Just give me some time. First, let me explain on the basis of equation. After that, I'll explain on the basis of content and concept. Please. So E2 plus EJ is equal to I2 into Z2. Why I took plus means that voltage is aiding, it is adding the existing rotor voltage. So from this, yes, E2 naught is equal to minus EJ plus I2 into Z2, right? So from this, S nu is equal to minus EJ by E2 naught plus I2 Z2 E2 naught. And we have seen this E2 I2 Z2 by E2 naught is S volt. Already you have seen this mathematically. I'm talking about this is S volt mathematically. S volt. So S nu is equal to S volt minus EJ by E2 naught. This is the new slip. Is this point clear? Confirm me. Confirm me. Right. See, we are going to discuss many points here. For example, E2 naught is equal to say 100 volts. 100 volts, let me consider. And the injected voltage per phase is say 50 volts. Then what will be the new slip? S nu is equal to S volt is how much? 0.05 minus 50 by 100. That is 0.05 minus 0.5. So it is minus 0.45. Then what is the value of new speed? NR new is equal to NS into 1 minus S nu, that is equal to 1000 into 1 minus of minus 0.45. Then you can see the speed is 1450 RPM. What is the speed of the motor now? 1450 RPM. This we call it as super synchronous speed. Of course, it will act as a generator, super synchronous speed. Right? So if you are injecting a voltage in phase with the existing rotor EMF, then we can get the speeds above rated, above synchronous. What is the rated speed? Earlier it was 950, and we are making the rotor speed to be 1450 RPM. We are making the rotor speed to be more than synchronous speed. So this we call it as super synchronous speed, right? The machine will be operating as a super synchronous speed. Then you may have a doubt, sir, how come
in case of an induction motor, the speeds can be more than synchronous when you are injecting a EMF. I'll tell. Up to here clear? Please confirm me. Confirm me. Right. So instead of injecting 50 volts magnitude, I'll inject 5 volts magnitude. For example, if I'm injecting 5 volts, if I'm injecting 5 volts, then what will be the S nu? It is 0.05 minus 5 by 100, then the slip will be 0. Then what is the new speed? It is 1000 into 1 minus 0, it is 1000 RPM. So this is nothing but your synchronous speed. Sir, how come in case of an induction motor, the rotor speed can be synchronous speed? Now, this is a very, very important question. Please try to be careful. So tomorrow, if anyone questions you, is it possible for a three-phase induction motor to operate with the speeds equal to ns? Then you have to give the blind answer that not possible in general. Why? Because as this motor works on induction principle, if the rotor speed is equal to the synchronous speed, the torque will be zero, the motor cannot rotate. There is no chance that the rotor can rotate with a speed equal to ns in general. Is this point clear? Is this point clear? Right. But is a bit of poison. But if it is a slip ring induction motor, and if the rotor circuit is also excited in addition to the stator side, in that particular case, in that special case, it is possible to operate an induction motor with the speeds greater than ns or even equal to ns. How come? Means the answer is, if there is no excitation given to the rotor circuit, then who is circulating the currents in the rotor conductors? Means it is only the EMF due to flux cuttings. So when we are not giving any excitation to the rotor circuit, whatever the current that flows in the rotor windings is due to the EMF induced in the windings due to flux cuttings. But when you are giving the excitation to the rotor circuit externally, then the current is decided by the resultant of the voltage due to flux cutting and the injected voltage. So it is true that when the rotor is rotating with synchronous speed, this E2 will be zero. Why? Because the flux cuttings will be zero. But still the rotor windings will carry current. Still the rotor windings will carry current due to that injected voltage, due to that supply voltage. And these current carrying conductors are under magnetic field produced by the stator field, and hence these conductors will produce a torque, and there is a chance that the rotor can rotate with a speed equal to ns. Why? Because the rotor is not excited only from stator side because of flux cutting. The rotor is excited separately due to a separate three-phase source, and these three-phase sources supplying the currents into the rotor conductors. Because of that current, the rotor can rotate with a speed equal to ns. So in this special case, the rotor can rotate with a speed equal to ns. I think this point is clear. Confirm me, all of you. Right. So this is basing on the equation. But what is that you are trying to do means C. What is that you are trying to do means C. If you see this electromagnetic torque equation, electromagnetic torque is equal to the rotor input power by omega s. And the rotor input power is equal to 3 E2 naught I2 cos theta 2. So here 3 E2 naught plus EJ into I2 cos theta 2. So here what is happening means, when you are injecting an EMF in the rotor circuit, so the rotor receives active power by two means. One is through induction principle from stator, it receives active power, and by conduction principle from the external source, it receives active power. So the rotor receives two active powers. One active power is from stator to rotor through induction. The other active power is directly fed to the rotor circuit. So the amount of active power fed to the rotor is increased. When the amount of active power fed to the rotor is increased, the torque which depends on that will also increase. Because of the increase in torque, the speed of the motor will increase. Like this, we can make the speeds greater than ns. So we can have super synchronous speeds also. I think this point is clear. Confirm me. So tomorrow if anyone questions, are by injecting a voltage in phase with the rotor circuit, what is that you are trying to do? Means you are injecting a active power into the rotor circuit. When you are injecting an active power into the rotor circuit, then the total active power received by the rotor will increase. Initially, when you are not giving any excitation to the rotor, so the rotor receives that active power from stator. Now it is receiving active power by two ways. One is through induction, the other one is due to conduction. And hence the total active power will increase, and hence the torque will increase. Like that, the speed of the motor will also increases. Is it clear? Confirm me once. Confirm me once. All right. Then what happened to power factor, sir? I agree. I'll explain what happened to power factor, sir. So one way we are able to improve the speed. What happened to power factor? I'll explain that power factor. Don't worry. All right. So if you see the phasor diagram, this is V1, this is I naught, this is I mu, this is phi r, this is E2. Now what is that we are trying to do? We are trying to inject a voltage in phase. This is ER. What is the phase of E2 and ER? Sorry, not EJR. First, let me write EJ. What is the phase of E2 and EJ? Both are same, right? Then what is the resultant? So resultant is ER. Then you can see ER, EJ and E2 all are in same phase. Same phase. Now, whatever the rotor current that is there, it has to lag when angle theta 2 with respect to ER. But here ER and E2 both are same. Then here, when that is same, this angle is also same. When this angle is same, even this angle is also same. When that angle is same, there is no change in that power factor. So the power factor will almost remain same. The power factor will almost remain same. So there will not be much change in the input power factor. The power factor will remain same, right? I hope this point is clear. Confirm all of you. Confirm all of you. Right. Sir, it is like a regenerative braking. I cannot call it as a regenerative braking. In case of regenerative braking, we don't give excitation to the rotor circuit. Please remember, right? Right, the power factor will remain almost the same. Now let me explain what is the true concept. Please see. See. So if I take this case, so what is the active power supplied from the stator to rotor? 10 kilowatts here. 10 kilowatts here. In addition to that, from the rotor side, I'm supplying 2 kilowatts of active power. Let me assume. Then what is the total active power set to the supplied to the rotor? 12 kilowatts. But what is the reactive power drawn from the source? It is almost the same. 2 kVAr reactive power is drawing. Then there is no much change in the power factor. Only the active power drawn by the rotor will change, and hence the torque which depends on that will change. Further, the speed will change. So there will not be much change in the power factors. I hope this point is clear. Confirm me all of you. Confirm me all of you. Right. Once again, I'll repeat. One or two students were asking, sir, can you please repeat once? Yes, I'll repeat. See, before to the speed control technique, I was trying to tell you that the speed of an induction motor cannot be varied in very wide ranges, keeping that ns constant. Because as this motor works on induction principle, keeping that synchronous speed constant, if you're trying to take the rotor speed away from ns, then the windings will get damaged. One more problem what we had with this induction motor is, as it is a single excited machine, the motor will always draw the lagging currents and operates at lagging power factor. Then, before to the speed control techniques, I told you that the speed of an induction motor can be controlled for below rated speed effectively, efficiently, satisfactorily using the V by F method. So in that V by F method, the performance of the motor will be satisfactory and we can control the speed of the motor effectively. But there in that case, it is not possible to improve the power factor. Why? Because in that case, as that motor is still excited from stator side, it will draw the lagging currents and the power factors will be always lagging in that. So there is no chance that the motor power factors can be made leading in that. And one more problem is whatever that V by F method we discuss, it is applicable only for below rated but not for above rated. Then the solution for that is using this EMF injection method, we can get the speeds below rated, above synchronous, below synchronous, and also the power factors can be improved. So for that, what is that we are trying to do means, in addition to giving excitation to the stator circuit, we are giving the excitation to the rotor circuit. But keep that in mind, at what frequency we need to give the supply means it should be always slip frequency. Now we have seen the first case. What is that first case? We are giving a three-phase excitation to the rotor frequency, a rotor circuit at a frequency of SF, and whose voltage is in phase with the existing induced voltage in the rotor circuit. In that case, the total active power fed to the rotor will increase. As a result, the torque will increase, and hence the power, the speed also increases. But as we are feeding only the active power into the rotor circuit, the reactive power drawn from the source will be almost the same. The power factors will be almost the same. I hope this point is clear. Confirm me, all of you. Confirm me. Right. Only few. What about others? Raise the hands. Right. Next one is, if I'm injecting an EMF in phase opposition. In phase opposition. So case 2 is, if an EMF is injected, if an EMF is injected in phase opposition. Phase opposition. Right? Opposition means it is 180 degrees phase shift. So if I'm trying to take this one as E2, then that injected voltage will be 180 degrees phase shift. Then the resultant voltage will be like this. EJ. Is it clear? Confirm me, all of you. Confirm me, all of you. Raise the hands. Right. So here let us go for the equations. What are the equations? E2 minus EJ is equal to I2 into Z2. So yes, E2 naught is equal to EJ, Y minus I have taken in phase opposition, I2 Z2. So from this, S nu is equal to S volt plus I2 Z2 by E2 naught. Then I take the same example, 0.05 I2 by I2 into Z2 by E2 naught, sorry. This is point, just 1 second. This is EJ by E2 naught. So this is 0.05, this is 0.5. Let me consider EJ is equal to 50, E2 naught is equal to 100. Let me consider. Then it is 0.55. Then what is the value of NR2? It is 1000 into 1 minus 0.55. So it is 450 RPM. It is much away from the synchronous speed. So these we call it as subsynchronous speeds. Subsynchronous speeds. Subsynchronous speed. So how the speed can be controlled means simple logic. Simple logic. What is that? If you take this equation for the rotor input power, it is minus. If it is minus, then what is the active power fed to the rotor? Decreases. What do you mean by that? See, if I take this circuit, so from stator, how much power is coming to the motor, rotor? 10 kilowatts, let me assume. Out of this 10 kilowatts, 2 kilowatts is taken away and it is fed to the source again. Then what is the active power fed to the rotor? Now it is only 8 kilowatts. Then the power fed to the rotor is reduced. Then the torque which depends on that will be reduced. The speed which depends on that will also reduces. Like this, we can get the speeds below synchronous, that is subsynchronous speeds. So tomorrow, if anyone questions you, or if you're injecting an EMF in phase opposition to the existing rotor EMF, then what happened to the speeds? So we get the speeds below synchronous, that is subsynchronous speeds. Then what happened to the power factors? We'll see. Or why the speeds will be reduced means when you're trying to inject a voltage in phase opposition, it looks like some of the active power fed to the rotor from stator through induction is taken back and it is given to back to the machine. As a result, the active power fed to the motor is reduced and the torque which depends on that is reduced and the speed is reduced. Like this, we can answer. Is it clear? Is it clear? Right. Done. Now let me go for the power factors. See. Right. How will power taken from the rotor, sir? It is looking like, why? Because it is 10 minus 2. Why? Because whatever the voltage you are injecting, it is in the phase opposition. As it is in the phase opposition, what is the RMS value of voltage fed to the rotor? Decreases. When the RMS value of the voltage decreases, what happened to that power? Decreases. Anonymous attendee. Is it clear? Is it clear? Right. Done. Now what happened to the power factor? I'll repeat, don't worry. What happened to the power factor? Now you're trying to inject in phase opposition. When you're trying to inject in phase opposition, then you can see this EJ is here. EJ is here with respect to E2 180 degrees. Then your ER will be here. Then with respect to ER, that angle will be again theta 2 and the angle that input angle will be again theta 1. There is no much change in the power factors. Only what is that going to change? It is only the speed. Why? Because the reactive power drawn from the source will remain same, right? Please go through this. Once again, I'll repeat. How to control the speed of an induction motor using EMF injection method. What is the meaning of EMF injection method? Means giving one more three-phase supply at a frequency of SF to the rotor circuit. Now in this case, this induction machine is supplied by two sources. One at a frequency of F to the stator, the other at a frequency of SF to the rotor. This machine, in this case, it is called as double excited induction machine. Why? Because stator receives a three-phase power from three-phase source. Rotor receives one more three-phase supply from the rotor side at a frequency of SF. Is this point clear? Confirm me. Raise the hands. Right. So here, how many possible cases I can have? Means I can have 4 possible cases. What is that possible case 1 or case 1 means? Whatever the voltage you are injecting or giving to the rotor circuit, if the phase of that voltage and the existing rotor voltage due to that flux cuttings, if both are same, then we call it as case 1. That means if you are injecting a voltage in phase with the existing rotor EMF, that we call it as case 1. Is it clear? Clear? Right. So when you are injecting a voltage in phase, then what is the total voltage in the rotor circuit? Increases. When the total voltage in the rotor circuit increases, what happened to the current? Increases. Then what happened to the torque? Increases. Then obviously what happened to the speed? Increases. So here we get the speeds more than rated, that is above synchronous, that is called as super synchronous speed. So if anyone questions you, in this case, is it possible to operate an induction motor with the speeds equal to ns? Of course it is possible. How? Means whatever the voltage you are injecting, EJ should be in such a way that the slip before injection, this ratio EJ by E2 naught should be same. Then these two will cancel out, the slip will be 0 and hence the motor can rotate with ns. In other way, as the rotor current is due to the phasor sum of E2 and EJ at NR is equal to NS, the E2 magnitude will be 0. But still, the external supply, the injected voltage is supplying the current into the rotor conductor, and hence the windings will carry current and the motor can run with a speed equal to NS. Is this point clear? Confirm me. Right. So it is something like when we are giving a voltage in phase with the existing rotor EMF, the active power fed to the rotor is increased. Why? Because what is the equation for that active power? The equation for the active power is E2 not I2 cos theta 2. So here it will be E2 naught plus EJ. Then what is the active power fed to the rotor? Increases. When the active power fed to the rotor is increased, then obviously what happened to the torque? Increases. Obviously what happened to the speed? Increases, right? But here what happened to the power factor means, as we are disturbing only the active power fed to the rotor, then the reactive power drawn from the source will remain same, and hence the power factor will be remaining same. Is this point clear? Confirm me, all of you. Confirm me. Right. So this is case 1, right? Done. What about that case 2? Case 2. So here we are injecting voltage in phase opposition. When we are injecting a voltage in phase opposition, it looks like some of the active power from the rotor circuit is taken back. As the amount of active power is taken back from the rotor circuit, then what is the active power fed to the rotor is reduced. The torque which depends on that will be reduced, and hence the speed will be reduced. But what happened to the power factors will be almost the same. Is this point clear? Confirm me. Right. Done. So one question is, if NR is equal to NS, say here there is no concept of motoring or generator. Please see, I can talk motoring or generator only when the motor is single excited, but it is a special case to control the speed. So when we are talking about the speed control technique, please remember that look only on the control of speed, not on the NR is equal to NS or something else. Please remember that. Is it clear? Confirm me, all of you. Confirm me, all of you. Right. Done. Now the question is, see, one of the student asked, sir, what is the why the reactive power will be constant? Why? Because there is no change in the power factor angles. When there is no change in the power factor angles, obviously there is no change in the so-called as reactive power drawn from the source. Please remember that. Done. So this is your case 2. So here we get the speeds below synchronous. Case 3. Please see. Case 3, very important. Case 3. What is that case 3 means? If an EMF at slip frequency after this, I'll give a cut short. Listen, is injected, shortcut I'll tell. Injected is injected at an angle 90 degrees leading. 90 degrees leading. In one of the textbook, instead of explaining all these things, he has given a shortcut method. That is your so-called as Nagaratan Kotari. What is that Nagaratan Kotari says? See, I'll tell that also in shortcut method. So you know, in resistance control, slip is directly proportional to R2, right? You know that. And NR is inversely proportional to slip. You know that. So when I'm talking about the first case, when you are injecting a voltage in the rotor circuit in phase, the total voltage is increased. When the total voltage is increased, the current in the rotor conductors are increased. It looks like when the currents in the rotor conductors are increased, the resistance of the rotor circuit is decreased. When the resistance is decreased, the slip will decrease. When the slip decreases, the speed of the motor will increase. Why? Because when we are injecting a voltage in phase, so the total current in the rotor circuit is increased. When the total current in the rotor circuit is increased, indirectly it says that the rotor circuit resistance is reduced. Because of that, the slip will be reduced. Because of that, the speed will be increased. The motor speed will be increased. Is this point clear? Confirm me. Confirm me. Right. In the second case, as you are injecting a voltage in phase opposition, due to the difference of voltage, the rotor current is decreased. When the rotor current is decreased, the resistance of the rotor circuit is increased. When the resistance of the rotor circuit is increased, the slip increases. When slip increases, the speed of the motor will decrease. So this is what that is given in your Nagratan Kotari, nothing more than that. Please remember. So he can compare these two, right? Is it clear? Confirm me. Is it clear? Confirm me. Right. So first case, speeds more than rated. Second case, speeds less than rated. First one is super synchronous. Next one is subsynchronous. I think it is clear. Confirm me. See, Anil Kumar Malhotra. I never said E2 naught is equal to 0. I told you that EJ by E2 naught, if it is equal to the slip value, then the difference will be 0 and the slip will be 0. Please remember that. Please, right? Please. Done. Next one is if I'm injecting a voltage at an angle 90 degrees leading. See, this is phi r, this is E2, this is your V1, and other things I'm not drawing. Now I'm trying to inject a voltage 90 degrees leading. This is EJ. When I'm injecting at an angle 90 degrees leading, so this will be ER. So with respect to this is I2 which will act when angle theta 2. This is your I naught. This time this is your I2 dash. Then this is I1. Then this is theta 1. You can see now the angle is reduced. When the angle is reduced, then obviously what happened to that reactive power drawn decreases. Obviously what happened to power factor increases. So here, if you are injecting a voltage at an angle 90 degrees, means what is that power you are feeding into the rotor circuit means reactive power. So leading wars, you are supplying reactive power. When you are supplying a reactive power into the rotor circuit, then the reactive power drawn from the source will decrease. Why? Because to produce a field, let us consider it is requiring 2 kVR. So the 2 kVR is initially drawn from source. Now here you are supplying one more reactive power into the source. Say you are supplying 1 kVR. For the total flux phi, then we need 2 kVR. 1 kVR is coming from the rotor side, then 1 kVR is drawn from the source. Then the amount of reactive power drawn from the source is reduced. As a result, what happened to the power factor? The power factor will be improved. So if you remember in case of a synchronous motor, if a synchronous motor is overexcited, what is the meaning of overexcited? When a synchronous motor is overexcited, so you are reducing the reactive power drawn from the stator side. When the reactive power drawn from the stator side is reduced, what happened to the power factor of the input? Increases. Similar to that, when you are giving the reactive power to the rotor of induction motor, what happened to the reactive power drawn from the source? Decreases. Obviously, what happened to the power factor? Increases. Is this point clear? Confirm me. Confirm me. Right. See, these are all something which you have to look into the machine and you imagine the machine. So equations, phasor diagrams will not tell anything. You have to imagine, oh, you are injecting at an angle of 90 degrees, means you are injecting reactive power. So as this machine is drawing the reactive power initially from the stator, when you are supplying from the rotor side, the reactive power drawn will be reduced and hence the power factor from the input will be increased. Is it clear? Confirm? Confirm? Right. So here the power factor will be improved. Then what happened to this speed? Speed, let me tell, speed. So here if you recall, yes, E2 naught plus JEJ, final I'll repeat, don't worry. So I know this is something like complicated issue, but still. EJ is equal to I2 into Z2. So S nu is equal to minus JEJ by E2 naught plus S volt. See, in the first two cases, we are adding arithmetically. What is the meaning of arithmetically? It is 0.05. It is something like 0.5. We are adding arithmetically. Is it possible to add a complex number or an imaginary number arithmetically to a real number? No. As it is not possible to add a complex number or imaginary number to a real number, so this real number will remain same. That means S volt will remain same. When S volt is remaining same, the speed of the motor will remain same. So in this case, it is not possible to vary the speed. Why? Because we are adding which power to the rotor circuit? Reactive power. Then active power drawn by the rotor will remain same. Why? Because the load is constant and hence the power factors and the speed will remain same. I hope this point is clear. Confirm me. Confirm me. So in the third case, what is that we can vary? We can vary the power factor, but not the speeds. I hope this point is clear. Last case and important case, basing on this, many time question was asked. Case 4. If an EMF is injected at an angle alpha leading with respect to E2. So if I do that, this is E2, I am injecting at an angle alpha leading. I think this is clear. Then how many components will be having? See, if you take this is A, this is theta. What is the component of A here? A cos theta, and this is A sin theta. A sin theta. So what is the component of that EJ here? It is EJ cos alpha. And what is the component of EJ here? EJ sin alpha. Is it clear? Confirm me. Confirm me. Right. Now, with respect to E2, you can say EJ cos alpha is in phase. So whenever we are talking about in phase, what is the power we are feeding into the rotor? Active power. And with respect to E2, this EJ sin alpha is quadrature, 90 degrees. So with respect to E2, if you are injecting at an angle 90 degrees, what is the power you are feeding into the rotor? Reactive power. So when you are feeding both active power as well as the reactive power, then due to this active power, the speed will change, and due to this reactive power, the power factor will change. In the last case, both speed as well as the power factors can be varied. I hope this point is clear. Confirm me. Confirm me. Right. So this is something about EMF injection method. Now let me update. After this, I'll give break. Let me update. Array, from my basics, from my BTech level of understanding, I know that a three-phase induction motor always operates with lagging power factor, drawing the lagging currents, and the speed of the motor should be always closer to ns, and hence a three-phase induction motors cannot be used for variable speed operation. Then I rule out this statement. I give the answers for that person like this. See, if whatever the motor you are talking, if it is a slip ring induction motor, then if I am having a three-phase variable frequency, variable voltage source, then if that source I can give it to the rotor circuit, then I can operate this induction motor for variable speeds. I can take out the rotor speed away from synchronous speed closer to zero, or I can make the rotor speed above synchronous speed more than ns. So I can operate both below synchronous, subsynchronous, above synchronous, super synchronous, and at the same time the power factor of the motor can also be varied. Why? Because using that rotor side circuit, rotor side excitation, we can inject both active power as well as reactive powers. When we are adding both active and reactive power to the rotor circuit, then the reactive and active power fed to the rotor circuit will change, and obviously the speeds and the power factors will change. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. But what is the main difficulty, main drawback we are having with this EMF injection method is, theoretically, I can say inject an EMF in phase, inject an EMF in quadrature, see that the frequencies are SF. Like that, theoretically, I can give the statements. Theoretically, we can go for the results. But if I want to inject a voltage exactly in phase at 180 degrees or 90 degrees, then the design of that controller, the design of that power electronic controller is complicated, and it is something like costly. So always I need to measure the phase of the rotor voltage, and with respect to that phase, I need to inject the voltage and also at the frequency of SF. The design of controller, it is complex and costlier. So that is the reason it is a costly and complex controller is required. I hope this point is clear. Confirm me. Right, done. So here drawbacks is costly and complex controller. Complex controller. So one student has texted, sir, in case 2, ER and EJ, you told. See, this is E2 Baba, and EJ is in phase opposition, and this is ER, E2 minus EJ, correct only. So this is, with respect to E2, EJ is in phase opposition, and this is ER, correct. So this is correct, right? Done. So any doubt in this, please confirm me, all of you, if you understood. All of you raise the hands. Right. So one question, sir, if I inject a DC, see, always I need a frequency whose frequency should be equal to slip frequencies. But if you're injecting a DC, the frequency of the DC will be 0. So that DC will not have any effect on the speed control. Please remember, so if you want to disturb the power fed to the rotor circuit, the frequency should be same as the induced frequency. Remember that. Please remember that. Right. Case 3, can you please explain, sir? Case 3 means, see Baba, I'm there, don't worry. Case 3 means, so with respect to E2, I'm injecting at an angle of 90 degrees. This is 90 degrees. Then what is the resultant of these two? This is the resultant of these two, ER. Now with respect to ER, that I2 will lag by an angle theta 2. So that theta 2 is the previous angle, it should lag with an angle theta 2. So to compensate this I2, there is one more current I2 dash. Then the resultant of I2 dash and I0 is nothing but your I1. We can see that I1 phasor is moving closer to V1. That means angle is reduced. So this is a mathematical expression, but what is the concept means, when you are injecting a voltage at an angle 90 degrees leading, that means to the machine which power you are feeding means a reactive power. When you are feeding a reactive power, then the reactive power drawn from the source will decrease, and hence the power factors will increase. Is this point clear? Confirm me. Is this point clear? Confirm me. Right, done. So we'll take some break. Anyhow, we'll be having question and answer session. We can spend time on that. Absolutely no issue. So last question, sir, can you please fourth point once again, right? Right. Fourth point once again. Ha, Baba. Fourth point means neither that EJ we are injecting at an angle 0, nor we are injecting at an angle 180, nor we are injecting at an angle 90, but at an angle of some alpha. That alpha may be between 0 and 180. So if it is 0 and 180, you are injecting both active power as well as reactive power. We know that when we inject active power, the speed will change, and we know that when we inject reactive power, the power factor will change. How can you say? See, this is alpha here. What is the component of Ej onto this E2? Ej cos alpha. What is the component here? Ej sin alpha. Now with respect to E2, Ej cos alpha is in phase, With respect to E2, Ej sin alpha is quadrature. So in phase means active power, quadrature means reactive power. Like that, we are adding active power as well as reactive power, and hence the power factor and the speed will be varying. Is this point clear? Right? Rawat. Right, done. So we'll take some break. After that, we'll see the last method, cascade connection. Then after that, we'll see the other topics. Right? We'll take some break.
Can you hear me, all of you? Raise your hands. Right. So this is something about speed control technique, right? The next one is single cascaded connection is there that we'll see at the end, right? There is no need to discuss as of now. Next one is, see, the leftover topics in this three-phase induction motor is the testing, right? So what is the testing? We'll see after the single phase induction motor, right? Please. Single phase induction motors. Induction motor, right? Done. So before I discuss this single phase induction motor, once again, let me go for the construction of a three phase. The basics, let me go back once again. After that, I'll come back to this single phase. So if you remember, in case of three phase induction motor, we have taken a frame, and inside the frame, we placed the core. Inside the core, we made slots. In the slots, we distributed the conductors of a three-phase windings with a space angle of 120 degrees electrical, right? So we have taken a three-phase winding, and the conductors of these three-phase windings are physically placed with a space angle of 120 degrees electric. Basing on the rotor construction, we saw two types of rotors. One is a cage rotor, the other one is a wound rotor. So I have taken a cage rotor now. A cage rotor now. Now when I give a three-phase excitation to this three-phase stator winding, then we saw the poles are formed in the stator core. Because of these poles, we have magnetic flux lines. As these poles are rotating, the flux lines also rotating. They cut the rotor conductors. As a result, an EMF is induced. Because of that EMF, there is one current. Because of that current, we have one more pole formation in the rotor core. As soon as these rotor poles are formed, they seize an opposite poles in the stator core. To align these rotor poles with the stator poles, the rotor starts rotating. But unfortunately, as the stator poles are rotating, to align these rotor poles with the stator poles, the rotor chases the stator poles, and hence a three-phase induction motor is a self-starting motor. So on one line, can I say, as the stator poles are rotating, to align the rotor poles, the rotor also starts rotating, right? This was discussed in a in a long discussion previously. As the nature of those stator poles are rotating, the rotor poles also rotate, and hence the rotor will rotate. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. See, one student wrote cascaded connection. I'll tell, don't worry. Right. Let me talk fresh. After that, I'll tell, don't worry. Cascade connection, it is a 5-10 minutes class. As the stator poles are rotating, to align the rotor poles, the rotor also rotates. So can I write? As the stator poles are rotating to align the rotor poles, the rotor poles, the rotor also rotates, also rotate. Hence, a three-phase induction motor is a self-starting motor. Is it clear? Confirm me. Is it clear? Confirm me, all of you. Oh, right. Just only few. See, this is not the new thing which I'm discussing now. Long back we have seen this, right? Just I'm recalling that's all, nothing more than that. Now what I will do means I'll take the same stator, I'll take the same stator, right? In the same stator, I place the core. I'll make the slots, and in the slots, I'll distribute the conductors of a single phase windings. So here, the difference what we are having in the stator of a three phase and the stator of a single phase means the stator of a three phase carries the conductors of a three phase windings which are physically spaced at an angle of 120, but whereas the stator of a single phase carries the conductors of a single phase windings which are distributed, right? This is the difference. Here also, basing on the rotor construction, we are having two types of induction motors. One is a cage type, the other one is a wound type. So these cage type single phase induction motors are widely used. The wound types are rarely used, right? So even the single phase induction motors are also classified as squirrel cage as well as slip ring induction motor basing on the rotor construction. Now, whatever the rotor I have used here in case of three phase, the squirrel gauge rotor, I'll take out that and I'll place it here. So can I say there is no separate construction of a squirrel cage for three phase and single phase. So whatever the rotor we are using for a three phase, the same rotor can be used for a single phase. The rotor construction is same for three phase as well as single phase. So it is not like a for a squirrel cage three phase, the squirrel cage rotor construction is different for a single phase. No, I can use the same rotor exchangeably for three phase or also single phase. Is this point clear? Confirm me. Confirm me. Right. Now this rotor, when I'm using in a three phase winding stator and when I give a three phase supply, then we saw that the rotor was rotating. The motor was rotating. Now here, what I'm trying to do means I'm trying to give a single phase excitation here. I'm trying to give a single phase excitation here. So because of single phase excitation, even in the stator core, we have poles. These poles induces an here poles in the rotor circuit, but very unfortunately, what is the nature of these poles? Stationary and they are oscillating. As these poles are stationary and oscillating, the rotor will remain stationary. In cut short, in one word or in one line, can I say, in case of three phase, as the stator poles are rotating, the rotor is also rotating. But whereas in case of single phase, as the stator poles are stationary, the rotor remains stationary, right? As of now, for you and for me, just to make you understand, in case of three phase, as the stator poles are rotating, the rotor rotates. But whereas in case of single phase, as the stator poles are stationary, the rotor also remains stationary. Is this point clear? Confirm me. Confirm me. Confirming? Yes. So here the stator poles are stationary or rotating? Stationary, and hence the rotor will also remain stationary. So here, as the stator poles are stationary, the rotor remains stationary. Remains stationary, right? Stationary. But this is not enough to tell why a single phase induction motor is non-self-starting, right? So now let me update. So if anyone questions you, or an induction motor is a self-starting motor or non-self-starting motor, then you are supposed to question him back whether it is a three-phase induction motor or a single-phase induction motor. If the question is a three-phase induction motor, then it is a self-starting.
If it is a single phase induction motor, then it is a non-self-starting motor, right? Please try to remember. Is this point clear? Confirm me. Confirm me, all of you. But this is not enough to tell why a single phase induction motor is non-self-starting motor. There is one theory which explains why a single phase induction motor is non-self-starting, and the theory is nothing but a double field revolving theory. So the double field revolving theory tells why this motor is non-self-starting. Now I'll be explaining double field revolving theory. Double field revolving theory. See, I told you already what is the difference between a theory and a law. Law is always true, and for law, there is no mathematical equation required. It is something like if you see something wrong, then it has to be penalized. For example, if you are breaking a traffic signal, and if you have been caught for that, you have to pay the fine for that. It is a law. And if you move a conductor in a magnetic field, then you can see an EMF is inducing that conductor. There is no need to prove mathematically that, but you can see experimentally the result is there. So a law doesn't need any mathematical proof. But when I'm talking about a theory, compulsorily a theory need a mathematical proof. So here I need to explain mathematically what is this double field revolving theory, right? Done. Now before to that, if I go back to this three-phase induction motor, I'll explain this three-phase induction motor mathematically. What is that? Whenever a three-phase supply is given to this induction motor stator winding, then we are having a resultant MMF which is rotating. This resultant MMF will produces one field, stator field, which cuts the rotor conductors, and EMF is induced. Because of this rotor EMF, there is one current. Because of this current, there is one more field, rotor field. The interaction of these two fields produces a resultant field, and because of this resultant field, there is one torque, and because of one torque, the rotor is rotating. So how many torques are acting on the rotor? There is only one torque. Because of that one torque, the rotor is rotating. If I'm calling myself as a rotor, see, because of this resultant field which is rotating in one direction, there is only one twisting effect. There is only one torque acting on me. So in which direction I'll move? I'll move in this direction. So how many rotating fields are there? You talk about the resultant. How many rotating fields are there? Resultant, one. Then how many torques are there? One. Because of the torque, one twisting force, the rotor will try to rotate. This was already explained. So in case of a three-phase induction motor, how many rotating fields? You talk resultant. There is only one resultant field. There is only one torque. Because of that one torque, the rotor will rotate. And hence a three-phase induction motor is a self-starting motor. Is it clear? Is it clear? Right. Now I'll be explaining why a single phase induction motor is non-self-starting motor using this double field revolving theory, right? Please. Now I'll consider stator with only main winding, only one winding, main winding or one winding. Please see all of you. Now I'll be considering a stator with only one winding. One winding. I'll consider the rotor here, right? As I told you that this double field revolving theory has to be proved mathematically. Why? Because it is a theory. So for a mathematical proof, what I'll do means I'll represent this winding with n cos theta. Don't ask all these things, you know. And I'm passing a current Im cos omega t. You know all these things, right? This is a squirrel cage rotor.
So when I pass this single phase currents into that single phase winding, then I'll have one MMF. That MMF I call it as the main winding MMF. Main winding MMF. That is N cos theta into Im cos omega. I'll write this one as Fm cos theta cos omega t. So if you see this MMF due to that single phase windings and single phase current, it is stationary and pulsating. Stationary and pulsating. This was already discussed. Now what I'll try to do means using the trigonometric expansions, I'm going to split this into two components. Two components. So what is that? Can I write cos A cos B into 1 by 2 cos A minus B plus 1 by 2 cos A plus B. I'm going to split this into two components. One is Fm by 2 cos theta minus omega t. The other one is Fm by 2 cos theta plus omega t. You can see mathematically there is no wrong in these two. So you can see these are mathematically correct. Is this point clear? Confirm me. Confirm me. Right. But already I told you in my previous classes, whenever you are coming across either cos theta minus omega t or cos theta plus omega t, that parameter, the term represent rotating. Why? Because with omega t, the theta also changes. With omega t and theta, the resultant MMF will be moving. So cos theta minus omega t represent a rotating one, and theta plus also represent a rotating one. Rotating. So can I say like this? The single phase stationary and pulsating MMF. See, already we have discussed what is stationary and pulsating in the RMF concept, please. The stationary and pulsating MMF, I can resolve into two components of rotating MMF. So how many rotating MMF I can visualize means I can visualize two rotating MMF. On what basis I can say two rotating MMF means in my previous classes, when I was explaining about the concept of rotating magnetic field, we have seen mathematically cos of theta minus omega t represent a rotating nature, right? Done. And here the coefficient of that cos represent magnitude. So what is the magnitude of that MMF? Fm by 2. And what is the speed at which it will rotate? Ns. So here also what is the magnitude? Fm by 2. And what is the speed at which it rotates? Ns. But the sad thing is they are not rotating in the same direction, but they are rotating in the opposite direction. Why? Because if minus, if I take it as a forward clockwise, forward or clockwise, then plus I have to take it as backward or counterclockwise. Counterclockwise. Clockwise, right? So how many rotating MMS I had? Two rotating MMS I had. Is this point clear? Confirm me. Confirm me. So can I say, can I tell what about others? I need all should raise their hands. So can I say, according to the double field revolving theory, the stationary pulsating single phase MMF can be resolved into the two components of rotating MMFs with equal magnitudes and rotating with the same speeds but in opposite direction. If one is rotating clockwise, the other one is rotating in counterclockwise direction. Is this point clear? Confirm me. Is this point clear? Confirm me. Right, done. Now here how many MMFs are there? Two MMFs. Now let us consider the first one, the forward MMF. I'll consider the first one, the forward MMF. I represent it as FF. As the nature of that MMF is rotating, then it will produce as one flux. Let me consider the first one. It is producing one flux, forward rotating magnetic field. Rotating magnetic field. What are the properties? It will have a magnitude of phi m by 2. And what is the speed at which it will rotate? Ns.
So then what is the speed at which this field will be rotating? This field will be rotating with a speed of ns. Don't ask why, it is already discussed. Then you can see this upper rotor conductors are stationary and the field is rotating. Because of that, what is induced in the upper half of the rotor conductors? EMF, rated as E to F. As the rotor circuit is closed, because of that, what flows? A current flows. The same three-phase concept I'm talking. So this cuts the rotor conductors. As a result, what is induced in the rotor conductors? EMF. And as the rotor circuit is closed, that induced EMF will circulate a current. So because of this current, there is one more flux, phi to F. So there is one more flux, that is phi to F. See, all this we have seen in the three phase, the same thing is applicable, phi to F. Then the interaction of phi 1 and phi 2F will produce as a resultant. Because of this resultant, there is one torque, forward torque, and because of this torque, the motor wants to rotate in forward direction, which is inversely proportional to slip. Why inversely proportional? At starting, S is equal to 1 high slip. So during high slip region, torque is inversely proportional to slip, right? So if this is the only torque acting on the rotor, then the rotor would have started rotating in forward direction. Now let me complete the remaining part here. So this rotor field and the stator field will interact to produce as a resultant field. Because of this resultant field, the rotor wants to rotate in which direction? Forward direction. If this is the only torque acting on the rotor, then the rotor would have started rotating in forward direction, like just like your three-phase induction motor. I'll tell you a similar example. If I'm calling myself as a rotor, see, if there is only one force which wants me to move in this direction, if this is the only force which is acting in this direction, because of that force, I can move only in this direction. But very unfortunately, if there is one more force acting on this in this direction, then there is no chance, that there is no guarantee that I can move in this direction, unless and until if the force magnitude in this direction is dominating this. Unfortunately, if both the forces are same and acting in opposite direction, then I cannot move. Then where I will stand, I'll stand in the same position. So according to the double field revolving theory, how many rotating magnetic fields are there now? Two rotating magnetic fields. Because of one magnetic field, we have seen that the rotor wants to rotate in forward direction. Up to here, clear? Confirm me. Right. Now I'll consider this one. This one. So because of this also, there is one field, but in which direction that field will be rotating? This field will be rotating in opposite direction. FB. And you can see these conductors are stationary and this field is rotating in opposite direction. And the field is rotating and the conductors are stationary. Because of that, there is one flux whose magnitude is phi m by 2 and which rotates in opposite direction. And I call that flux as phi 1b and I name it as backward rotating magnetic field. Why? Because it is moving in opposite direction. And one more thing, let me consider the slip is ns minus nr by ns. I'll take the reference. Even the forward torque also wants to rotate in which direction? Say forward direction, ns minus nr by ns. So here sf is equal to s. It is like this. Done. Now let me come back. So as this mmf is in opposite direction, then that will produce a field in which direction? Opposite direction. And I call that one as phi 1b. As these conductors are stationary and this field is rotating, see, everything is applicable like three-phase induction motor. There is nothing like separate to be discussed here. So these conductors will have voltage, and because of this voltage, there is one current. Because of this current, there is one more field, phi 2b, rotor rotating magnetic field due to that backward mmf. So this will produce as one EMF, and this EMF will circulate a current. So because of this current, there is one more flux. Then the interaction of those two fields will produce as a resultant. Because of this resultant, there is one torque, right? And this torque wants the rotor to rotate in which direction? Opposite direction. In which direction? Opposite direction. So there is a resultant. So because of this resultant, there is one torque. So this torque is acting in opposite direction. Now you please conclude. In case of three-phase induction motor, how many torques are acting on the rotor? There is only one torque. Why? Because how many rotating MMFs are there? Only one rotating MMF is there. Because of that, only one rotating MMF, one rotating field, you talk resultant, one rotating field, and how many torques are acting on the rotor? There is only one torque acting on the rotor. Because of the torque, the rotor starts rotating. Rotor starts rotating. But whereas in case of a single phase induction motor, according to the double field revolving theory, how many torques are acting on the rotor means there are two torques are acting on the rotor. Why? Because according to the double field revolving theory, the stationary and pulsating MMF can be resolved into the two components of rotating MMF, and these two rotating MMF will produce as two rotating magnetic fields resultant, and these two rotating magnetic fields are producing two torques acting in the rotor, and those two torques are given by TF and TB, right? Now, in which direction that secondary torque is acting means it is acting in opposite direction. So can I say SB is equal to NS plus NR. It is acting in opposite direction by NS. And already you have seen that NS plus NR by NS, I can write it as 2 minus S. I can write it as 2 minus S. Don't ask how, it was already been derived. So it is inversely proportional to 2 minus S. So how many torques are acting on the rotor means two torque. It is something like two forces are acting. Then what is the resultant force means? The resultant torque is equal to the difference of forward torque minus backward torque. Backward torque. Now at starting, you know that NR is equal to 0, slip is equal to 1. Then forward slip will be 1. Then backward slip, it is 2 minus S, again will be 1. Then the magnitudes of forward field will be equal to the magnitudes of the backward field. The magnitudes of the forward torque are equal to the magnitudes of the backward torque, and the resultant torque acting on the rotor is 0. And hence, a single phase induction motor is non-self-starting motor, right? So can I imagine like this? If I'm calling myself as a rotor, right? So here, how many forces are acting on me? Two forces. I take this side as a clockwise force and this side as a counterclockwise force. So unfortunate thing is that starting the force in this direction, magnitudes are same, but they are acting in opposite direction. Then what is the resultant force acting on me is 0. Then where I stand in the same position. The same thing is happening here. According to the double field revolving theory, the single phase stationary pulsating MMF can be resolved into two components of rotating MMF. Just like in case of your three-phase induction motor, there is only one field. So here how many fields we can imagine? Two rotating MMF. These two rotating MMF produces two rotating magnetic fields, and these two rotating magnetic fields produces two torques. Very unfortunately, the magnitudes of the two torques are same, but they are acting in opposite direction, and hence the net torque acting on the rotating part is 0. That's the reason the single phase induction motor is non-self-starting motor. You can just watch, you can imagine, you can just test this. What is that? If you just raise the hand, there is one fan. So what is the motor we are using in that fan means a single phase motor, induction motor. There is a capacitor. I'll tell you the role of a capacitor after some time. You just remove that capacitor and don't give any supply to that fan. If you try to rotate with your hand, you can see the shaft is rotating freely. You can see that blades, if you rotate, they will rotate freely. But once you give the excitation, you stop it. Then after that, you give the excitation. Then if you see the fan will not rotate. Why? Because you have removed the capacitor, the fan will not rotate. Then if you try to check If you try to move with the hand, then you can see it looks like that the shaft got struck. It got struck. It doesn't mean that it got struck. It's something like because of this rust, it looks like it got struck. It is not like striking. Why? Because at starting, two torques are acting, and the magnitudes of these two torques are same, but they are acting in opposite direction. That is the reason they are locking the rotor not to rotate in this direction and in this direction. So it looks like it is locked. It looks like it is blocked. The motor cannot, the shaft cannot rotate. But if you disconnect the supply, then if you just rotate with the hand, then you can see this will rotate just like freely it can rotate. So, but when you stop again, if you give the supply, why it is not rotating means it looks like it is locked. Why? Because the two forces are acting in opposite direction. The resultant torque acting in the rotor is zero, and hence the motor cannot start rotating, right? So finally, can I say, I can imagine a single phase induction motor as on the same shaft, two three-phase induction motors are connected. One is excited with the phase sequence ABC, other is excited with the phase sequence ACB. So these two three-phase induction motors torques are in opposite direction, right? Magnitudes are same, and hence they are not making the motor to rotate. The same thing in a case of a three-phase induction, in case of a single-phase induction motor, the stationary and pulsating MMF can be resolved into the two components of rotating MMF. These two rotating MMF produces two rotating magnetic fields, and these two rotating magnetic fields will produces two torques, and the magnitudes of those two torques are same, but they are acting in opposite direction, and hence the resultant torque acting on the rotor is zero. That's the reason a single phase induction motor is non-self-starting motor. I think this point is clear. Confirm me, Allah. Right. Now, the same single phase induction motor has that same double field revolving theory has given the solution for this. What is the solution means? See that the slip is not one. When slip is not one, the magnitudes of the forward field and the backward fields will not be same. The field becomes unbalanced. When the field becomes unbalanced, due to this unbalanced field, there is a torque acting on the rotor. Because of that unbalanced torque, the rotor will start rotating. What do you mean by that? See, I consider this motor as a 6-pole motor. Let me consider. It is a 6-pole motor excited with a 50 hertz supply. Let me consider. What is the value of NS in this case? It is 1000 RPM. 1000 RPM. Let me say. So with the help of a hand, I'll twist. We say 10 RPM. 10 RPM. Twisting. Then what is the slip? So S is equal to 1000 minus 10 by 1000. So it is equal to 0.99. Then what is the forward slip? It is 0.99. What is the backward slip? It is 2 minus 0.99. It is 1.01. You can see forward slip is not equal to backward slip. The forward magnitude is not equal to the backward magnitude. Then hence the forward torque magnitude is not equal to backward torque. The resultant torque is not zero, and in the forward direction the torque will rotate. It is something like if you turn the rotor with your hand, then the field and the direction will start dominating the other field. When one field is dominating the other field, the field becomes unbalanced. Why? Because it is assumed that there are two fields rotating in opposite direction. But if you give an initial twist, this field will start dominating the other field, and that resultant field make the field to rotate in one direction. Now, this field will be rotating in one direction, which is having the forward minus backward difference. Because of this rotating field, it will cut the conductor EMF like torque will produce, and that will make the rotor to rotate. So can I say, if I give an initial twist in any of the direction, the torque, the field in the direction which dominates the other field, the field becomes unbalanced. That means the strength become unbalanced. So in which direction the strength is more means in forward direction the strength will be more coming to the backward. So as the strength in one direction is more compared to the other, the field becomes unbalanced. When the field becomes unbalanced, the forward rotating magnetic field will be dominating the backward rotating magnetic field, and its looks, the resultant will be moving in forward direction, and hence, because of that flux cutting EMF current torque, the rotor will start rotating. It is something like this. I'm calling myself as a rotor. See, at starting, these two fields are same. Now one person is coming in this direction and he's trying to add to this field. Then in which direction I'll move? I'll move in this direction only. But it doesn't mean that in this direction there is no force. There is a force acting. But when compared to this force, as there is another force added, that force and this force will be adding up, and the force in this direction will be more, and I'll try to move in this direction. Is this point clear? Is this point clear? Right. So whenever I try to give an initial twist in one of the direction, the strength of the field in that particular direction will increase, and because of the increased strength, then that field will be dominating the other field, and the field becomes rotating in one direction. Because of that, there is a torque acting. But very unfortunate thing is this torque is due to unbalanced field. Why? Because we are having forward component as well as backward component. Because of this unbalanced field, in the torque we'll be having two components, forward component and backward component. The resultant will be the difference of forward field and the backward field. So in case of an induction motor, whenever you try to give an initial twist, then you don't have only one torque acting on the rotor. There will be two torques are acting on the rotor. Because of the difference of those two torques, the rotor will continues to rotate. But luckily, in case of an induction motor, how many torques are acting? There is only one torque acting. Because of the torque, the rotor will continues to rotate. But here, in case of an induction motor, single phase, there will be two torques are acting. So if you give an initial twist, one torque will be dominating the other torque. The field becomes unbalanced. Because of that, the rotor will continues to rotate. Is this point clear? Confirm me. Right. So here the main point to be noted is in case of three phase, the field is balanced. In case of three phase induction motor, the field is balanced. Balanced field. Please remember these points are all required. Tomorrow when I'm talking about if a supply is unbalanced supply, if it is a single phase, we are going to discuss all those miscellaneous concepts. For that I need all these things, please. In case of three-phase induction motor, the field is balanced. What is the meaning of balance? There is only one rotating field. Only one rotating field. So at any instant, you can see there is only one field. That is called as a balanced field. But whereas in case of single phase, there are two fields, but you should make the field to be unbalanced. How to make the field to be unbalanced? By giving a twist in any direction, forward direction or backward direction. If you give a twist in any direction, then the field in that particular direction will start dominating. The strength will be dominating the other. So because of that, the resultant field will be in that particular direction. Because of that resultant field, which is rotating, that will have a torque acting on the rotor. In that direction, the rotor will try to rotate. But how many torques will be there in that? There will be two torques. One is forward torque, the other one is backward torque. Because of the difference, the motor will continues to rotate. Now you please tell me, in case of three-phase induction motor, the torque is due to a balanced field, but whereas in case of a single-phase induction motor, the torque is due to unbalanced field. So who is making that field to be unbalanced means by giving some initial twist in one of the direction, you are making that field to be unbalanced. Whenever the field is made unbalanced, because of that unbalanced field, the rotor will continues to rotate. But whenever I'm talking about unbalanced field, how many torque components will be present? Two torque components. One is forward component, the other one is backward. As one field is dominating the other field, one torque will be dominating the other field, other torque, the motor will continue to rotate due to the difference. Is this point clear? Confirm me. Confirm me. Right. Right. Done. So can I say like this? Can I say like this? Can I say like this? According to the double field revolving theory, according to the double field revolving theory, the single phase stationary and pulsating MMF can be resolved into the two components of rotating MMF, and these two rotating MMF will produces two torques. Very unfortunately, the magnitudes of those two torques at starting are same, but they are acting in opposite direction, and hence the resultant torque acting on the rotating part is zero. Therefore, a single phase induction motor is a non-self-starting motor. But however, if you give a twist in any of the direction, then the field in the direction will dominate the other field. It makes the field to be unbalanced. Due to this unbalanced field which is rotating, the motor will start rotating. But how many torque components will be present means two torque components. One is the forward torque component, which is having a slip of SF. The other one is 2 minus S into F. I think this point is clear. Confirming. Right. Done. Now let me draw the torque slip characteristics of a single phase induction motor. Right. Please see here. I'll take this is S is equal to 1. You know the equation for the torque. What is the equation for the torque? So it is, if I neglect the stator side, it is 180 by 2 pi ns S E2 naught square into R2 by R2 square plus S X2 naught whole square. This is the equation for torque. Basing on that, I'll draw the torque. I'll draw torque. This is the torque for 0 to 1. Then I increase the value of slip from 1 to 2. That means here I substitute 1.01, 1.02 like that. If I plot, then I'll get the slip extended up to 2 here. The slip extended up to 2. So these are the characteristics up to 2. Is this point clear? Confirm me. Is this point clear? Confirm me. Confirm me. Right. Done. Now I'll take the image of this two-fold image. What is the two-fold image? I'll flip like this and I'll draw like this, a two-fold image. Like this. It is the two-fold image. Now, if I want to calculate the resultant torque at say 4% slip, 4% slip. So the resultant torque at 4% slip, if I want to calculate, just tell me. So I need to calculate the forward torque at a slip of 0.04, and I want to calculate the backward torque at a slip of 2 minus 0.04, that is 1.96. Then I need to find out the difference between these two. I'll get the resultant torque there. Is this point clear? Confirm me. Is this point clear? Confirm me. Right. Then see. See, I want to calculate the torque at say 4% slip. 4% slip. Let me say. So if I want to calculate the torque at 4% slip, then I need to calculate this torque at 4% slip. The other one is 2 minus 0.04. I have to calculate this torque. That is the torque at 1.96. Then I have to find out the difference. You can see this torque and this torque both are same. So if I want to calculate the resultant, I have to subtract this minus this. I'll get the resultant torque due to that forward slip and backward slip. Once again, so if you consider, say I'm trying to draw the torque slip characteristics of a single phase. I want to calculate the torque at 4% slip. If I want to calculate the torque at 4% slip, so this is the 4% slip. Let me consider. What is the magnitude of torque at 4% slip due to forward field? This is the magnitude of torque due to 4% slip due to forward field. Is this point clear? Confirm? Right. What is the magnitude of torque due to backward field? It is 2 minus S. That is I need to find out this torque. So I need to subtract this magnitude from this magnitude, this magnitude. So instead of doing like this, so I'll subtract this. This is why, because this at 4% slip, this at 1.96% slip, both are same. Is this point clear? Is this point clear? Like that, I'll be finding out the torques. So the resultant will be somewhere here, somewhere here. Like this, I can plot for all the values at different slips. Then if I want to calculate the resultant at S is equal to 1, you can see at S is equal to 1, the forward torque is this much, the backward torque is this much. Both the torques are same, then you can see it is 0. So here the resultant will be like this. Resultant will be like this. Like this. Is this point clear? Is this point clear? Torque slip characteristics of a single phase induction motor. Is this point clear? Once again, raise the hands. Right. So here the points to be noted is, if I'm trying to draw separately, in case of three phase, if I'm trying to draw separately, please see. In case of three phase, the characteristics will be like this. This is for three phase induction motor. But whereas in case of single phase, like this, you can see at S is equal to 1, due to single phase, the torque is 0, starting torque is 0. But in case of three phase, that starting torque is not 0. So this is for three phase and this is for single phase. So can I say, in case of three phase induction motor, the electromagnetic torque is 0 only at one speed, which is speed when Ns is equal to, when Nr is equal to Ns, or slip is equal to 0. Why? Because at Nr is equal to Ns, the relative speed between field and conductors will be 0, the flux cuttings will be 0, and the torque will be 0. But whereas in case of a single phase induction motor, that electromagnetic torque is 0 at two speeds. One is when Nr is equal to 0, the other one is when Nr is closer to Ns. It is not at Ns. Why? Because in case of a single phase, the torque is not due to only one field. The torque is due to the difference of forward field and backward field. If I take these equations, this is inversely proportional to S minus inversely proportional to 2 minus S. If I substitute S is equal to 0, then it will be having very high magnitude minus some small magnitude. That means there will be some resultant torque. Because of that, the motor torque cannot be 0 at S is equal to 0. So it will be having a negative value there. It will be having a negative value. Then the machine will be acting as a generator when S is equal to 0 in case of a single phase motor. So these are very, very important questions. Please see. In case of a three-phase induction motor, the electromagnetic torque is 0 only at one speed, that is when Nr is equal to Ns. Why? Because this torque is due to a balanced field because of only one rotating magnetic field. But whereas in case of a single phase induction motor, the torque is not due to a balanced field, it is due to unbalanced field. So as the torque is due to unbalanced field, there will be two torques acting on the rotor. One is forward torque and the other one is a backward torque. So the resultant torque will be due to the difference of forward and backward torque. And this resultant torque is 0 at two values of rotor speed. One is when Nr is equal to 0, the other one is when Nr is closer to Ns. Closer to Ns means who decides that Ns? Closer to Ns. Closer to Ns means I don't know, but who decides? It decides dependent on the resistance, leakage, reactance of the motor windings, right? So this is something about three phase and single phase. Confirm me. Confirm me. Right. So can I say like this? In case of, I'll write a note here. Please note down this. I'm writing. In case of three-phase induction motor, electromagnetic torque is due to balanced field, and this torque is zero only at ns. But whereas in case of single phase induction motor, the torque is due to unbalanced field, and this torque is zero at two rotor speeds, one at nr is equal to 0, the other at nr is closer to ns. At ns, single phase induction motor acts as induction generator, negative slip, induction generator. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. I'll repeat once again. Please go through. So I'll be having class up to 9. Please, after that, the doubt session will be there. Don't worry. So in case of, just if I'm trying to tell on the basis of poles, in case of three-phase induction motor, the stator poles are rotating, and hence the rotor also starts rotating. And hence a three-phase induction motor is self-starting motor. But whereas we have seen in case of a single phase winding, those stator poles are stationary and pulsating, and hence the rotor will remain stationary. So it is a conversation between the rotor and the stator poles. In three phase, as the stator poles are rotating, the rotors will also rotate. But whereas in case of single phase, the rotor says, when you are stationary, where is the question that I will be rotating? I will also remain stationary. So this is only for make you understand. But what is the true reason means, in case of a three phase, whenever we give a three phase supply to the stator winding, we have one stator field which rotates with ns. This cuts the rotor conductor EMF current. Because of that current, there is one rotor field, and these two fields will get interacted. And because of this interaction, there is one resultant field, only one rotating field resultant. Because of that, the rotor will continue to rotate in that particular direction. The field in that case is balance. Balance means there is only one field rotating. Because of that, the rotor will rotate. But whereas in case of single phase induction motor, according to the double field revolving theory, the single phase stationary pulsating MMF, we have resolved into how many components of rotating MMF? 2. These two rotating MMF will produce as two rotating fields. These two rotating fields produces two torques. But very unfortunately, the magnitudes of those two torques are same, but they're acting in opposite direction. And hence the resultant torque acting on the rotating part is 0. That is the reason a single phase motor is non-self-starting. But if you give an initial twist, then the strength, the field strength in the direction will dominate the other field strength. The field becomes unbalanced. Because of that unbalance, there is a rotating nature of the field that will make the rotor to rotate. But how many torques will be acting on that? Two torque, forward torque and backward torque. You can see from the torque slip characteristics only at S is equal to 1, the torque is 0. But in this region, the torque value is not 0. So the torque value is positive. Because of that, the rotor will try to rotate. So you have to see that S is not equal to 1, then the motor will continue to rotate. I hope this point is clear. Confirm me, all of you. Confirm me, all of you. Right. Now the question, one of the student has told, sir, how to give a twist? How to give a twist? So can you show upward and backward? You can see these are the curves, right? Then how to give a twist, right? The question is, You can give it with the hand, but not feasible, practically not acceptable. If I bring a fan, say I'm using a single phase motor, when I switch on, every time I cannot step into the bed and I'll take a stick, I cannot rotate. So it is a meaningless approach to start the motor. Then what are the starting methods we are having means the starting methods is starting methods. So here as the name says starting methods. So what is the purpose of starter in this case means the purpose of starter in case of a single phase induction motor as the name says is to start the motor, starting the motor. So you can write as the name says, as the name says is to start the motor. Start the motor. Start the motor means not like continuously rotating for only initial twist. Start the motor for a initial twist. For a initial twist. Then what are the possibilities we are having means one is a pony motor. Second one is auxiliary winding. Auxiliary windings. Auxiliary windings. Then now question comes. What is a pony motor? Pony is nothing but a small motor. A small motor with starting torque. So here what I will do means pony motor. Let me draw. Pony motor. Get ready. I will ask one question. Let me see how many will answer. So I'll take a single phase induction motor here. Say this single phase induction motor I'm using for a fan. I'm using for some fan like this, right? I'm using for some fan like this. Let me show. So when I give a supply to this, say this is a shaft which is been fitted to the roof, right? Cellar. Then if I give a single phase supply, then is it possible for that fan to rotate? No. Why? Because the torques are. So if you look into this, so how many torques will be acting on this? Two torques. One is the forward torque, the other one is the backward torque. The resultant torque acting on the rotor is zero, and hence the fan will remain stationary. It will not start rotating. Is this point clear? Confirm me. Confirm me. Raise the hands all of you. Right. Now what I will do means on the same shaft, I'll mechanically couple one pony motor, a small pony motor, a small motor, a two-phase motor which is having a starting torque. Small pony motor. PM means pony motor. And I'll give the excitation to this pony motor based on the motor which I'm using. Excitation I'm giving. So this pony motor has starting torque. Now say it is having a forward torque. So this is the torque of a pony motor. You can see this torque and this torque will add up, and this torque will be more compared to the backward torque, and hence this forward torque will be dominating the other torque and the motor will continue to rotate. So whatever the initial twist that is required, the pony motor will try to give. Once it starts rotating, then you can see when S is not equal to 1, then the motor has the torque. Then the motor has the torque. So the motor torque will be increasing, the motor torque will be raising. So only the initial twist that is required. Once the motor start picking up the torque, then you can disconnect the supply to this motor nearly 70 to 80% of the speed. Then the motor can rotate by its own torque. So whatever the initial twist that is required, that is given with the help of a pony motor. So once motor picks the speeds, picks the speeds, then the supply to that pony motor is disconnected. Then the motor can rotate by its own torque due to the difference of forward and backward torque. Is this point clear? Confirming? Confirming? Now the question is, are only in backward or forward? In any direction. If you twist in forward direction, it is forward. If you twist in backward, it will be in backward direction. You can check that. So this is the pony motor starting. But what is the main problem with this pony motor starting is this is not a feasible way of starting the motor. For example, say if you want to have a induction motor, single phase induction motor. I am supplying a single phase induction motor. You came to me You ask, you give one single phase induction motor, I want to use for fan application, say. Then I say, this is the motor single phase, this will not rotate. But if you want make this motor rotate, you have to use this motor. I'll say, these two motors you should purchase. Then you will say, no, I don't need, please get out. What is this? You say, this is a motor which I need, and this is the motor which you need to use to start the motor. I don't want, please leave it. So this type of motor is not feasible. And one more thing is that pony motor will be there on the shaft continuously. As a result, the mechanical losses will be more, overall efficiency of the set will be reduced. So for that, we don't use this pony motor starting in most of the single phase induction motor starting methods. That's the reason. If you raise the head, you cannot see a pony motor on the shaft, right? Is it clear? Confirm. Confirm. Right. The other one is auxiliary winding starting. Auxiliary winding starting. Very, very important. Auxiliary winding starting. Auxiliary winding starting. Now I'll ask one question. Please get ready to answer it. Auxiliary winding starting. Please answer to this. See, with only one winding, the motor is not starting. Why? Because forward torque and backward torque are making the rotor to remain stationary. But when I'm having auxiliary winding and when I'm passing a current through that auxiliary winding, then the motor will start rotating. Now, can you please tell me what is that logic or magic the auxiliary windings are doing, auxiliary windings currents are doing to make that motor to rotate? What is the logic? What is it that auxiliary windings and auxiliary winding currents are doing to make that start? Please tell me. Two phases, 90 degrees, net RMF. Resultant flux is increase in one direction. Phase displacement, phase shifting, create RMF, 90 degrees phase shift. It is self-starter, right? Changing into two phases, split phase, making more inductive, 90 degrees, two phase machine at starting, auxiliary winding, main winding are 90 degrees apart, two fluxes, it will produce a additional flux. Yeah, resultant torque is not zero, yes. Yeah, please enough, don't tell, right, don't text, right, enough, don't text, enough. Now I'm trying to explain what is the role of auxiliary windings and auxiliary winding currents in making that single phase induction motor to start. I'm trying to explain that. Please see. After this, we'll go for the doubt discussion. Please see. If I take this main winding, after this we can go for a doubt discussion. That is the main state. So this is the main winding, right? I'm representing this winding as n cos theta, right? So this is the rotor. Let me consider a squirrel gauge rotor. Let me consider. So through this main winding, I'm passing a current Im cos omega t. Then because of these main windings and main winding currents, I have one MMF. Already we have seen. It is Fm cos theta cos omega t. I can split this into two components. What are those? Fm by 2 cos theta minus omega t plus Fm by 2 cos theta minus omega t. So how many rotating MMS we had now? Two rotating MMS. I show that here. One is in forward direction Fm by 2 cos theta minus omega t. The other one is in the backward direction Fm by 2 cos theta plus omega t. Up to here clear? Confirm me. Right. Now in addition to this, what I'll try to do means in the same stator, I place one more winding with the same turns at an angle 90 degrees. And I call this one as auxiliary winding. And through this auxiliary winding, I'll supply one more current and the current with respect to main winding will have a time angle of 90 degrees. So this is n cos theta minus 90. So I'm representing that mathematically with a space angle of 90 degrees. So this is the auxiliary winding. This is the auxiliary winding, right? So because of this auxiliary winding and auxiliary winding current, there is one more MMF. What is that? Auxiliary winding MMF. So if I'm trying to write finally Fm cos theta minus 90 cos omega t minus 90. If I simplify this, Fm sin theta sin omega t. If I'm going to divide this, it is Fm by 2 cos theta minus omega t minus Fm by 2 cos theta plus omega t. So again, how many rotating MMFs I am having? 2 rotating MMFs I am having. Is this point clear? Confirm me. Confirm me. Right. It is only mathematics. I'm not doing any logic here. Mathematics. Please raise the hands, all of you. Right. So if I can modify this, so you can see, I'll change this minus to plus, and here I carry forward that minus here. Right. I'm changing that minus to plus. I'm carrying forward that minus to that magnitude. So how many rotating MMFs we have due to these auxiliary windings and also auxiliary winding currents? 2. So one is Fm by 2 cos theta minus omega t. Other one is minus Fm by 2 cos theta plus omega t. Is it clear? Confirm, all of you. Is it clear? Confirm, all of you. Right. Now once again, you please check, all of you. Please see. I'm changing this minus to plus, right? When I'm changing that minus to plus, then the direction of this field has to be reverse. Why? Because I have changed the magnitude, reverse. Right? Is it clear? Confirm me, all of you. Is it clear? Confirm me, all of you. Right. Then if I take omega t is equal to 0, a instant of starting, giving excitation. If I take omega t is equal to 0, we can see Fm by 2 cos theta minus omega t, Fm by 2 cos theta minus omega t will add up, and the resultant will be Fm cos theta minus omega t, and these two will cancel out. The field in this direction will be 0. Like that, when I increase the time to 1, again those two will add up, these two will cancel out. So at every instant of time, the backward MMF due to that main winding will be cancelled out. Then how many rotating MMFs will be there? Only one. Then how many fields will be there? Only one. The field becomes balanced. Only one field means the field becomes balanced. Because of that only one field, there is only one torque acting. Because of that one torque, the rotor will continue to rotate. My question was to you people, why with auxiliary windings and auxiliary winding currents, the motor is starting means your answer has to be like this. So whenever we place an auxiliary winding and whenever we pass current through the auxiliary winding, just like the main windings and main winding currents, the auxiliary winding and auxiliary winding currents are also producing two rotating MMFs. And out of these two rotating MMFs, one MMF is completely aiding the forward MMF due to main, and other MMF is completely cancelling out the backward MMF due to main. And hence, there is only one rotating MMF which produces only one rotating field, balanced field. And because of that, there is only one torque. Because of the torque, the motor will start rotating. I hope this point is clear. Confirm me, all of you. So can I write a point here? Please, can I write a point? With auxiliary windings and auxiliary winding current, just like main winding and main winding current, there are two rotating MMFs. There are two rotating MMFs, right? Out of this, one rotating MMF will aid the forward MMF due to main winding, and the other MMF cancels the backward MMF due to main winding, and hence only one rotating MMF, only one rotating field, one torque, and hence motor rotating, starts rotating, rotating. I think this is clear. Confirm me, all of you. Confirm me. If my question is, what are the conditions for auxiliary winding and auxiliary winding currents means, then you have to answer that. With respect to main windings, the auxiliary winding should be placed at an angle of 90 degrees. The auxiliary winding current should have a time angle of 90 degrees. These are the conditions, right? So we have discussed what is a role. What is a role means, just like the main windings, auxiliary windings are also producing two rotating MMF. Out of that, one is aiding the forward MMF, the other one is cancelling out the backward MMF. And hence there is only one rotating field, there is only one torque, because of that the motor will start rotating. I hope this point is clear. Confirm me all of you once. Right, right. As I said, I'll stop at 9 or stop. See, one small request, Baba, a small request from my side. So tomorrow our class will start at 4. Please try to cooperate with me. Please, those who are having college, please tomorrow for my sake, you sacrifice, right? In afternoon session, you please try to attend from 4 for tomorrow's sake, please. And our class will continue till our syllabus ends, right? Please. Is it clear? Confirm me, all of you. Raise the hands. If you permit me, raise the hands. Right. So please cooperate with me for tomorrow's sake, right? So we'll have the class from 4, right? I'll tell the schedule manager to reschedule from 4. Then we'll have the class till we complete the syllabus, right? Thank you. So for today, I'll stop, but class is not over. The next doubt session is there. I'll continue. Just wait. Right, right, right. Yeah. So for tomorrow, you please try to delay your dinner also, right? Otherwise, I'll give the break at 7:30. You can have a dinner during that time. One of the student has mentioned, right? Anyhow, I'll just attend this questions. Those who are raised the hands, right? Sai Charan Reddy. Sai Charan Reddy.
Hello,
Can you?
sir.
Ah,
Sir, in EMF injection, in case one, sir, like same phase.
In phase, not same phase. If you're injecting a voltage in phase, yeah, please.
Yeah, yes, sir, in phase.
Mm,
Yes.
yeah, please ask what is.
Sir, if NS is equals to sir, if NS is equals to NR, then SE2 will be zero, no, sir. That like a running EMF.
Not running, that induced EMF.
EMF at running.
Yeah, let me finish. Okay, your question is, sir, when NR is equal to NS, so the EMF that is induced in the rotor windings due to flux cuttings will be zero. Absolutely correct. But you know that the rotor windings are separately connected to another source, and that source will be supplying the currents into that winding. And those current carrying conductor placed under magnetic field will experiences the force, because of that the rotor will rotate. Understood? So who is forcing the current means the supply voltage will be supplying the current. Sai Charan Reddy. Is it clear?
Okay, sir. So we can say that the injected EMF supplies the injected current also.
No, it is not the injected current, the excitation which we are giving to the rotor circuit. We are naming it as injected voltage that is supplying the rotor currents. Understood?
Okay, okay, sir. Sir, but yeah, yes, sir.
Mm.
Sir, but this magnitude will be different, no, sir,
No, the
from
magnitude,
SE2.
no, the magnitude will be same. Why? Because the magnitude has to remain same. Why? Because the load on the motor is constant, right?
Okay, okay, sir.
When the motor is constant, the electromagnetic torque should remain.
Constant.
Then current flowing through that should remain.
Constant.
Yeah, like that.
Okay, okay, sir.
Understood?
Yes, sir.
Yeah, please. What is the next
Sir,
question?
when we supply like EMF injection, then relative speed increases.
Yeah.
Then you told that active power, how it increases, sir? Active power.
See, if you take the rotor circuit, right? The rotor windings are separately excited here, not the stator winding. So you are
Okay,
giving the
sir.
excitation. You are giving the excitation to which windings? Rotor windings or stator winding?
Rotor winding,
EMF.
sir.
What is the equation for power fed to the rotor? What is the equation for
Power
power
fed to
fed?
the E to not
E2,
I2 into I2 into
not E2. It is
hello, sir.
3. Yeah. 3 E2 not I2
3 I2 square R2 by S.
or 3
R2 by
E2
S. Yes, sir.
or 3 E2 not I2 cos theta 2. Correct?
Yes, sir.
So this is the power which is coming to the rotor from stator through induction principle, right?
Yes, sir.
Now in addition to that, you are adding one more voltage EJ. Then what is the total voltage to the rotor circuit? 3 E2 naught plus EJ into I2 cos theta 2. So whatever the 3 IJ I2 cos theta 2 is there, that is the power that is directly fed to the rotor winding.
Okay, okay, sir. Sir, for the same case, if we consider the NR is equals to NS,
Mm-hmm.
uh, that is, if we assume that after giving the injected EMF, the rotor is running at synchronous speed.
Mm-hmm. Yeah. See,
So now E2 not will here E2 not is not SE2 not. Okay, sir. Okay, sir.
E2 naught will not change. E2 naught will be fixed. Only SE2 naught will change. See, I'll tell.
Yes, sir.
See,
In
I'll tell.
rotor equation. Yes, sir.
You understood this, Sai Charan Reddy?
Sir, in power fed equation, power fed rotor equation, it is not SE not, it is each not only, so it is differ.
Your voice is not that much clear. Some disturbance is coming. You can please rectify. Yeah, now please tell. You are clear?
Yes, sir.
Right. Fine.
Sir, sir,
Yeah.
initially at the time of introduction class, when the flux cut the rotor conductor, then E2 I2 will induce. After that, I2 will come now, sir.
First E2
Yes, sir.
not.
This is complex only. Yes, sir. E2
See,
not.
Sai Charan Reddy, a lot of disturbance is there from your side. You can call me on my number. Okay. Otherwise, you rectify your network. You call me again.
Okay, sir.
Yeah, Kumar.
Sir, good evening, sir.
Good evening, Baba.
Sir, in frequency control method, sir, speed control.
Okay.
Uh, sorry, sir. Uh, sir, EMF injection method is there, sir.
Okay.
In that condition, case one and case two may so in phase and out of phase of EMF injected, right?
Yes. In phase.
And out of phase for case one, case two.
Mm.
So as in phase reactive power is applied, so P rotor input is increased.
Mm.
So
Yeah. Yeah. Please ask.
so we can get a speed over above the synchronous speed.
Yes. Absolutely correct.
Sir, in that case also I2 is increased, right?
See, initially I2 will increase, but at steady state I2 will remain same. See, I'll tell you one thing. See, I'll tell. See, Kumar, see. If this is your rotor voltage, E2,
Yes,
let
sir.
me say 10 volts. Let me say 10 volts.
Yes.
That is SE2 naught is equal to say not 10 volts. Let me take 5 volts for convenience.
Okay.
Is 5 volts. I have not injected any voltage to the rotor circuit.
Yes, sir.
It is short. Say let it be something like 1 ohm. This is understood.
Yes.
So I'll take E2 naught is equal to something like 100 volts and slip is equal to how much? 0.05. Then SC2 naught is equal to how much? It is 5
5
volts.
volts.
Correct? What is the
Yes, sir.
value of current here? It is
5
5
amps.
by 1. It is how much? 5 amperes. Correct?
5 amps. Yes,
Then
sir.
electromagnetic torque is directly proportional to current square. That is 5 square.
Yes.
Now say you are injecting a voltage here.
Yeah.
Say in aiding. So you are injecting 5 volts in addition. Let me say.
Yes.
Then what is the current now? I2 will be 5 plus 5 will be how much? 10. 10 by
5.
1. 5 plus 5 by 1.
Sir, we have. Okay. Okay.
10 volts. That is 10
Okay.
by 1. 10 amperes. Correct?
Yes. Yes.
So because of this 10 amperes, what happened to the torque?
100.
Increases.
Increases.
When torque increases, what happened to the speed? Speed
Speed. Speed means
increases.
increases.
When speed increases, what happened to slip?
Decreases.
So the slip starts decreasing.
Yes.
The slip starts decreasing. When slip starts decreasing, what happened to S into E2 naught value?
Decreases.
Decreases. So up to what level that slip will start decreasing means again the current becomes 5 amperes. Why? Because the torque should remain same. Why? Because the load torque is
Constant.
constant. So up to what level the slip becomes means the slip becomes 0. When slip becomes 0, S into E2 naught becomes
0.
0. Then current becomes
5 amps.
again the motor torque becomes
Same as it is.
load torque. So it will reduce up to 0 slip. Then the current will become same. Is it clear now, Kumar?
Sir, then the speed is also same. Speed.
See
What
how
about?
can slip is changing na in order to make that SE2 naught,
Sir,
right?
as slip is 0, what about how we get NR, sir? Or NS?
See now who is supplying the current now? This 5
Rotor
volt.
engine.
This is supplying the current. Now the current carrying conductors are placed under magnetic field. They will experience as a force. When slip is 0, what is the speed?
So in that case, the speed is NS.
Yes, in this case the speed is ns.
So in phase, if I inject 10 ohms also, it may be NS.
No. How can you say? If you are injecting 10 volts, it is 5 plus 10 by
15
1,
amps.
15 amperes. Then,
Okay.
so the voltage should become 5 volts. For the voltage
Oh,
should become, the slip becomes negative.
negative.
Then the speed becomes greater than ns.
Okay.
Understood now?
I understand.
Right. Okay. Clear,
So
Kumar?
here current is constant.
Current has to become constant. Why? Because the load is constant, the motor torque should be constant. For that, the current should become constant.
Okay.
Understood, Kumar?
Yes, I understand.
Right. Okay.
Thank you, sir.
Right.
Sir, another question.
Yeah, please.
Uh, so, uh, here we say that for active power injection is not right, right?
We cannot say active. See, it is right only. Why? Because only which parameter is changing?
Uh, Torque is constant means active power also constant, right?
See, finally, torque is constant, Baba. The motor torque is equal to load torque, correct? Finally.
Yes.
But initially, what is that the torque is raising means which power you are feeding?
Okay, in that case, active power is.
Yeah, understood.
Sir, what I'm thinking is that we know active power is equal 3 E2 naught into I2 into cos theta 2.
Yes.
So similarly, we can say reactive power as 3 E2 naught into I2 into sin theta 2.
Okay.
So here I2 is also changing. That's why we say that active power we 5 to 10 amps. So active power starting high and then came back to zero.
Normal. Correct.
Similarly, I2 is increasing. Reactive power also changes, right?
Yes, changes. Why? Because no, reactive power, how can you change, Baba? Phi R is directly proportional to V by F. You are changing any input voltage and input frequency parameters.
No.
Then how can you change that magnitude of that flux will change? No. When it is not changing, how the reactive power drawn from the source will change? It will not change.
Not drawn from the source, sir. Here in rotor side.
It will change. Rotor circuit parameters will change. Whenever the current changes, the magnetism will change, the flux linkages will change. Yes, it will change.
Okay.
But I am talking with respect to stator side. There is no change in the reactive power drawn from the stator.
Okay, so with respect to stator side, no change.
Yeah, understood. I told only with respect to stator, not with respect to rotor.
Okay, sir.
Understood?
Sir, in frequency control method, above rated and below rated speed, both cases ohmic losses are increases, right?
No. In below rated, how the ohmic losses will increase? In below rated, Ns minus Nr is constant. That means the relative speed between field and the rotor conductors is maintained constant. Flux cutting.
Only flux variation, sir.
See, the relative speed will remain same, na? Flux is maintained constant. V by F is kept constant in the first case.
Not in V by F method, sir.
Then?
Only flux variation method.
In the above rated. In above rated, as you said, yes, everything will change. It is unsatisfactory control. Flux will
below
change.
rated also ohmic losses are there.
In below rated, in pure frequency control, we have ohmic losses. But in V by F, there is no ohmic losses. Ohmic losses will.
V by F, okay, sir, I understand. But my doubt is in pure frequency control method.
In pure frequency control, for above rated and below rated, the currents will be more. The ohmic losses will be.
Sir, as a frequency increases, currents increases. As frequency decreases, also currents increases.
Yeah, why? Because whenever the frequency decreases, what happened to cores?
I understand those relations, sir, one by one.
Then what is it?
But frequency increases and decreases. Both cases, current increases means.
Why? Because in the first case, when the frequency decreases, what happened to flux magnitude?
Frequency increases.
When flux increases, magnetizing current drawn from the source
increases.
Then no load current drawn from the source
increases.
Input current drawn from the source
increases.
Then what happened to that ohmic losses will also increases. Is it clear?
Whereas in same year also, as flux frequency increases, flux decreases, IMU decreases, I0 decreases, I1 also decreases, ohmic loss decreases because.
But that total current I1, it is V minus E. That means that I2 dash is increasing, I0 is decreasing. I agree.
Yes,
but
sir.
What happened to that I2 dash?
So based on those relative amount, we say that increases.
Yes.
Okay, sir.
Understood, Kumar.
And understood. Thank you, sir.
Right. Yeah, Vishnu Ajit.
Sir, it is regarding the last auxiliary winding, sir.
Yeah, you can ask any doubt, Baba. I am there. Not only regarding auxiliary, any content. Yeah, please.
Sir, in this last one, it was like after splitting the sine Fm sin theta sin omega t, we got it as Fm by 2 cos theta minus omega t minus Fm by 2 cos theta plus omega t.
Yeah.
You even marked it as a backward field.
Yeah, this one is cos theta plus omega t. I marked it as backward field. Yeah.
Sir, but the thing is, then afterwards you said that this minus, I am taking it as an opposite sign.
Yeah, just only for mathematical proof, I took that minus to plus. I have changed
Sir,
that that is
uh,
minus.
okay, sir. And so in practically that will not happen, sir.
So in practically what is happening means the auxiliary windings and auxiliary winding currents are producing one more field which are opposing the backward torque due to backward field due to the main winding. As a result, that is cancelled out. In other way, you know what are the conditions to produce a rotating magnetic field with a two-phase windings and two-phase current. This is what happening here. So they are producing one single field. When they are producing one single field means the backward field due to the main winding is cancelled out.
Okay, sir. Okay, sir. If you add these two, okay, correct. They're getting cancelled.
Yeah, if you add these two, they get cancelled. If you add these two, it is something like this.
Okay, sir. So only the resultant will be in one particular direction.
One rotating field, one torque, because of that it will rotate.
All right, sir.
Understood? Right?
Yes, sir. Okay.
Right.
Thank you, sir.
Right. Right, Rahman.
Hello, sir.
Rahman, please.
Sir, EMF injection third case, please examine one time, sir.
In third case, when you are injecting at an angle 90 degrees, what is the power you are injecting into the rotor circuit? Reactive power.
Reactive power.
Yeah. In the first
Sir.
two cases, if you go to that slip nu is equal to slip volt plus EJ by E2 naught or
You do not.
S volt minus EJ by E2 naught. You are going
Yes,
for
sir.
an arithmetic sum. These two values are being added.
Yes, sir.
But in the third case, it is something like a complex number.
Okay, sir.
So with respect to first two cases, we are adding the numbers arithmetically. In the third case, it is a complex number. Is it possible to add a complex number to a real part?
No, sir.
No. So that means the real part will remain unchanged. As a result, the speed will be unchanged. But practically there is some changes, but the changes can be neglected.
Okay, sir.
Rahman, understood?
Okay, sir. Okay, sir.
Right, Baba. Right.
At the slip.
Just 1 second, Rahman. Yeah, Rahman, continue. Rahman, continue. Rahman,
Torque split characteristics for single. Hello, sir.
Yeah, please.
Torque split characteristics for single phase induction motor.
Yeah, this one. You can see, Rahman.
Yes.
Yeah, you can see on the board.
Yes, sir. Yes, sir.
Any doubt you have on that?
Sir, at the time you say in the two cases that it will become 0.
Yeah, see, when NR is equal to 0, this is torque magnitude. This torque magnitude and this torque magnitude are same, but they are acting in opposite direction.
Opposite direction.
So what is the resultant torque at S is equal to 1? 0.
0.
Right. Then if I take at NR is equal to NS, then I can say the torque is not 0. Why? Because one torque is inversely proportional to S, another torque is inversely proportional to 2 minus S. The torque cannot be 0 there. Then at the speeds closer to NS, it will be 0. Who decide means the resistance parameter, the leakage parameter. Understood?
Okay, sir. Yes, sir.
Right.
Thanks.
Right. I think people are hungry. They had been to dinner. No one is raising their hands. Yeah, Imtiaz Pasha. Yeah, Pasha.
Good evening, sir.
Good evening, Baba.
Sir, I have doubt in case 3 if EMF is in injection mechanism, no, sir.
Yeah. Imtiaz Pasha.
Sir, from the source we are taking the reactive power in normal case. In case 3, we are also taking from the reactive power from the
rotor side. Yeah, rotor is feeding reactive power now.
In that case, reactive power is increased, no, sir?
So no, it is leading, right? So this is lagging. So this leading and lagging will be cancelled out. So initially if it is drawing 2, this is leading minus 1. So 2 minus 1 will be 1. So 1 will be drawn from the source now. As a result, what happened to the power factor? This is not lagging. Instead of leading, if you inject lagging, then the input power factor will still decrease.
Okay, I thought both are lagging, sir.
No. This is leading. I wrote leading. Now you can check the notes. It is leading. It is not lagging. You
Yes,
can
sir.
check that.
Yes, sir.
Understand?
Yes, sir. Sir, one more, sir.
Hmm.
Sir, normally, if the rotor speed more than synchronous speed, that time we can call as generator, no, sir.
Yeah, I told you that it will act
Yes,
as
sir.
a generator. But when we are talking about speed control, let us concentrate only on speed.
If it is double excited, then it is called only motor.
Yeah, if it is a single excited machine, and in that case, if the rotor speed is made greater than synchronous speed, then in that case you can call it as a generator. But here the rotor is separately fed. So in this we are not supposed to call it as generator, right? You let us talk only, even if it is supplying the power, you call it as only motor.
Okay, sir. Okay, sir.
Understood?
Yes, sir. Yes, sir.
Right. Clear?
Yeah, yes, sir. Clear, sir. Thank you.
Right. Right. No one is raising the hands. I'll stop for today. Anyhow,